Close your eyes, breathe slowly. Tonight we descend into the Earth itself, to the places where the planet's interior breaks through its own surface in fire and ash and rivers of molten rock, where the deepest forces of a 4.5 billion-year-old world announce themselves with a violence and a beauty that no other natural phenomenon can match. Volcanoes have shaped every continent, every ocean floor, every atmosphere this planet has ever possessed. They buried cities and built islands. They caused famines on the other side of the world and painted sunsets that lasted for years. They created the conditions in which life first emerged, and they have the capacity, on their largest scale, to threaten the civilization that life eventually produced. This is the story of the volcanoes, the fires beneath the world. This is explored during sleeping. Fact 1. What a volcano actually is, the Earth speaking. A volcano, in its most fundamental definition, an opening in the crust of a planetary body through which molten rock, volcanic ash and gases escape from a magma chamber below the surface, is not, as it is sometimes imagined, an anomaly in the structure of the Earth, a malfunction or a wound in an otherwise stable planetary body, but rather one of the primary mechanisms by which the Earth performs the essential functions of its own geology. Cycling material between its interior and its surface, releasing the internal heat generated by the radioactive decay of elements present since the planet's formation, and reshaping the surface of the world in ways that have, over the 4.5 billion years of the Earth's existence, produced every continent, every ocean basin, and every atmosphere the planet has possessed. The word volcano derives from Vulcan, the Roman god of fire and the forge, whose mythological workshop was believed to lie beneath the island of Volcano in the Aeolian Islands north of Sicily, from which the island's characteristic smoke and fire were explained by the ancients as the exhaust of a divine blacksmith at work beneath the Earth. The specific reality of what a volcano is proved, when scientists eventually understood it, to be considerably more extraordinary than the mythology. At the center of the Earth lies a solid inner core of iron and nickel approximately 1,200 kilometers in radius, surrounded by a liquid outer core of similar composition, whose convective motion generates the planet's magnetic field. Above the core lies the mantle, a layer of rock approximately 2,900 kilometers thick that is solid in the mechanical sense, but capable, over geological timescales, of flowing like an enormously viscous fluid, driven by the heat rising from below. It is in the upper portion of the mantle and the lower crust that the magma, molten rock, dissolved gases and suspended crystals, that feeds volcanic eruptions originates, accumulating in magma chambers whose specific location, size, and composition determine the character of every eruption the surface above will ever experience. A volcano is, in the most literal sense, the Earth breathing. Fact 2. The plate tectonics connection, why volcanoes are where they are. The distribution of the world's volcanoes across the surface of the Earth is not random, not a scattering of geological accidents placed without pattern across the continents and ocean floors, but one of the most eloquent expressions in nature of the specific theory that transformed the earth sciences in the 20th century and gave humanity, for the first time, a coherent understanding of why the planet's surface looks the way it does. The theory of plate tectonics, which holds that the Earth's outer shell, the lithosphere, is divided into approximately 15 major and several minor rigid plates that move relative to each other at rates of between 1 and 10 centimeters per year, driven by the convective currents in the mantle below, and whose interactions at their boundaries produce the earthquakes, mountain ranges, ocean trenches, and volcanic chains that define the geography of the living planet. The overwhelming majority of the world's active volcanoes are located at the boundaries between tectonic plates, where the specific nature of the boundary determines the specific character of the volcanism that results. At subduction zones, where one plate dives beneath another into the mantle, as the Pacific plate does beneath the North American plate along the western coast of the Americas, the subducting plate carries with it ocean water and sediment that, as the plate descends and heats, releases fluids into the overlying mantle wedge, lowering its melting point and generating magma that rises through the overlying plate to produce the explosive, silica-rich stratovolcanoes of the Pacific Ring of Fire. At mid-ocean ridges, the vast underwater mountain chains where tectonic plates are pulling apart and new ocean floor is being continuously created. Less explosive, fluid basaltic lava wells up from below in a process of seafloor spreading whose scale and whose continuity, persisting for hundreds of millions of years, has shaped every ocean basin on the planet. And at hotspots, isolated plumes of unusually hot mantle material that burn through the overlying plate regardless of its position relative to plate boundaries. A third and particularly fascinating type of volcanism produces the island chains of Hawaii, the geothermal landscape of Yellowstone, and the extraordinary volcanic province of Iceland, whose specific position directly above a mantle plume and simultaneously on the mid-Atlantic ridge, makes it one of the most volcanically active places on Earth. Fact 3. The Ring of Fire, a circle of volcanoes around the Pacific. The Ring of Fire, the horseshoe-shaped zone of intense seismic and volcanic activity that encircles the Pacific Ocean basin, running from New Zealand northward through Indonesia and the Philippines, continuing along the eastern margin of Asia through Japan, the Kuril Islands and the Kamchatka Peninsula, crossing the Aleutian Islands to Alaska, then descending southward along the western coast of the Americas through Canada, the United States, Mexico, Central America. And the length of South America to Tierra del Fuego is the single most volcanically and seismically active region on the surface of the Earth, and the physical expression on the largest scale of the consequences of the Pacific Plate's interactions with the surrounding tectonic plates that encircle it. The Ring of Fire contains approximately 75% of the world's active volcanoes, more than 450 individual volcanic systems, whose combined history of eruptions constitutes the dominant volcanic narrative of the planet's recent geological past. It is responsible for approximately 90% of the world's earthquakes, including the largest earthquakes ever recorded by modern seismological instruments, and the specific relationship between its seismic and volcanic activity is not coincidental but causal. The same subduction processes that generate the magma feeding the ring's volcanoes also generate the tectonic stresses that produce its earthquakes and the tsunamis that those earthquakes trigger. The specific volcanoes of the Ring of Fire include some of the most famous and most dangerous on Earth: Mount St. Helens in Washington state, whose catastrophic eruption on May 18, 1980 killed 57 people and removed 400 meters from the mountain's summit in a lateral blast of unprecedented violence in the modern observational record; Mount Pinatubo in the Philippines, whose 1991 eruption was the second largest of the 20th century; Krakatau in Indonesia, whose 1883 eruption produced the loudest sound in recorded human history; and Mount Fuji in Japan, the most photographed and most culturally freighted volcano on Earth, whose perfect symmetrical cone has defined the Japanese aesthetic relationship with natural beauty for 1,000 years. To stand anywhere on the Ring of Fire is to stand on geology that is actively, dynamically alive. Fact 4. Types of volcanoes, the many shapes of fire. The popular image of a volcano, the symmetrical, cone-shaped mountain with a crater at its summit from which lava fountains and ash clouds periodically emerge, captures one common form of volcanic structure, but fails entirely to represent the extraordinary diversity of shapes, sizes, and behaviors that the geological processes of volcanism produce across the full range of the Earth's volcanic systems. The specific shape of a volcano is determined primarily by the composition of its magma, above all by the magma's silica content, which controls its viscosity, and by its dissolved gas content, which controls the explosiveness of its eruptions, and the range of volcanic forms that result from the variation of these parameters spans scales and geometries that challenge any simple mental image. The stratovolcano, also called the composite volcano, is the classic cone-shaped mountain of popular imagination, built up over thousands of years by alternating layers of lava flows, ash deposits, and pyroclastic material into a steep-sided symmetrical structure whose specific form reflects the moderately to highly viscous, gas-rich magma that produces explosive eruptions capable of building substantial cone heights. Stratovolcanoes include some of the most famous mountains on Earth: Fuji, Rainier, Etna, Vesuvius, and the volcanoes of the Andes, and their specific tendency toward explosive, violent eruptions makes them the most dangerous category for human populations in their vicinity. The Shield volcano, built from repeated eruptions of low viscosity, low-gas basaltic lava that flows easily across the landscape before cooling, producing broad, gently sloping structures that resemble a warrior's shield laid flat, is the largest category of volcano by volume, represented most magnificently by Mauna Loa in Hawaii, whose total volume makes it the largest volcano on Earth by mass. The caldera, formed not by the accumulation of erupted material, but by the catastrophic collapse of a volcano's summit into an emptied magma chamber following a massive eruption, produces some of the most dramatic landscapes on Earth, including the caldera of Yellowstone, whose specific dimensions reflect a volcanic system of a scale and a power that makes every other volcano in the continental United States appear modest by comparison. Fact 5. Magma and lava, the difference that matters. The distinction between magma and lava, two words that refer to the same material in two different states of its existence, is one of the foundational concepts of volcanology and one of the clearest expressions of how the specific context in which a geological material exists determines both its name and its behavior. Magma is molten rock while it remains beneath the Earth's surface, contained within magma chambers, moving through conduits and dikes in the crust, or pooling in the reservoirs whose gradual pressurization eventually drives volcanic eruptions. Lava is the same material once it has emerged at the surface, whether as a flow across the landscape, as a fountain from a volcanic vent, or as the fragmented projectiles of an explosive eruption. The behavior of lava at the surface, how far it flows, how fast it moves, what structures it creates as it cools, and how dangerous it is to anything in its path, is determined by the same compositional factors that determine the character of the magma below: its temperature, its silica content, its dissolved gas content, and the specific mix of minerals it contains. Basaltic lava, low in silica, high in temperature, low in dissolved gases, is the most fluid of the common lava types, capable in extreme cases of flowing at speeds of up to 60 kilometers per hour on steep slopes, producing the broad flat flows that build shield volcanoes and the spectacular lava rivers that have made the eruptions of Kilauea in Hawaii among the most photographed volcanic events in history. Andesitic and rhyolitic lavas, higher in silica, lower in temperature, higher in dissolved gas content, are far more viscous, moving slowly or barely at all, and building up the pressure in volcanic conduits whose eventual explosive release produces the catastrophic Plinian eruptions that define the Ring of Fire's most dangerous volcanoes. The specific textures that lava develops as it cools, the ropey, folded surface of Pahoehoe lava, the rough, clinkery surface of our lava, the spectacular hexagonal columns of basalt formed by the slow, even cooling of thick lava flows, are among the most beautiful and most scientifically revealing features of the volcanic landscape, each one a record of the specific conditions under which the Earth's interior was briefly exposed to the surface world. Fact 6. Pompeii, the city that stopped. The eruption of Mount Vesuvius on the 24th of August, 79 CE, the two-day volcanic event that buried the Roman cities of Pompeii, Herculaneum, Oplontes, and Stabii under meters of volcanic ash and pyroclastic material, killing an estimated 2,000 people in Pompeii alone, and preserving beneath the deposits a snapshot of Roman urban life in the 1st century CE of such extraordinary detail and completeness that it remains, nearly 2,000 years later, the single most important archaeological site for the understanding of daily life in the ancient Roman world, is the most famous volcanic disaster in human history, and the event that more than any other has shaped the popular understanding of what volcanoes do to the civilizations in their path. The eruption began with a column of ash and pumice, the Plinian column, named after Pliny the Younger, who observed it from across the Bay of Naples and left in his letters to the historian Tacitus the earliest detailed eyewitness account of a major volcanic eruption in the written record. That rose to an estimated height of 33 kilometers before collapsing in a series of pyroclastic surges. Fast-moving avalanches of superheated gas, ash, and rock fragments that descended the slopes of Vesuvius at speeds of up to 700 kilometers per hour and temperatures exceeding 300 degrees Celsius, killing every living thing in their path within seconds. The people of Pompeii who had not evacuated before the pyroclastic surges arrived did not burn to death, as was long assumed, but died almost instantaneously from the thermal shock of superheated air, their bodies preserved in the specific positions of their final moments by the ash that buried them, creating the void casts that archaeologists from the 19th century onward have filled with plaster to recover the most intimate portraits of death that the ancient world has left behind. Among the most haunting of these casts is the figure of a man who died shielding his face with his cloak, a woman clutching an infant, a dog still chained to its post. The city they inhabited, its bakeries with bread still in the ovens, its walls covered in political graffiti, its brothels with their painted menus, its wealthy houses with their frescoed dining rooms, was preserved so completely that walking through its excavated streets today is the closest experience available to any living human being of what it felt like to be alive in a Roman city 2,000 years ago. Fact 7. Krakatau, the sound heard around the world. The eruption of Krakatau, the volcanic island in the Sunda Strait between Java and Sumatra, whose catastrophic paroxysmal explosion on the morning of August 27, 1883, remains one of the most powerful volcanic events in the entire historical record, produced, in its climactic explosion at approximately 10 o'clock in the morning, the loudest sound ever recorded in human history. A detonation of such extraordinary acoustic energy that it was heard clearly on the island of Rodriguez near Mauritius, more than 4,800 kilometers away, and detected by barographic instruments at recording stations around the world, with the pressure wave generated by the explosion circling the globe not once, but at least 4 times before its energy was finally dissipated. Scale of the physical destruction wrought by the Krakatau eruption was matched in its human consequences by the tsunami it generated, a wave or series of waves produced by the collapse of the volcanic edifice into the sea that struck the coastlines of Java and Sumatra, with heights estimated at up to 37 meters, destroying 165 coastal towns and villages and killing approximately 36,000 people, the overwhelming majority of the eruption's total death toll. The material ejected by the eruption, approximately 21 cubic kilometers of rock and ash, was distributed by the upper atmosphere around the globe, producing one of the most spectacular series of atmospheric optical effects in the modern historical record. Vivid, multicolored sunsets visible from London to New York for months after the eruption, caused by the scattering of sunlight by the fine ash particles suspended in the stratosphere, and a measurable reduction in global average temperatures of approximately 1.2 degrees Celsius that persisted for 5 years. The eruption destroyed most of the original Krakatau island, whose collapse created a caldera on the seafloor. In 1927, a new volcanic island emerged from the sea within the original caldera, Anak Krakatau, the child of Krakatau, which has been intermittently active ever since, reminding the populations of Java and Sumatra that the volcanic system responsible for the most destructive eruption in recorded Indonesian history has not finished its work. Fact 8. Iceland, the island born of fire. Iceland, the North Atlantic island of approximately 103.0 square kilometers, whose entire landmass is the direct product of volcanic activity, sitting directly above both the mid-Atlantic ridge and the Iceland mantle plume in a combination of geological circumstances that makes it the most volcanically productive landmass on Earth per unit area, producing approximately a third of all the lava that has erupted on the Earth's surface in the past 500 years. Is the most complete and most accessible example anywhere on the planet of what the interior of the Earth looks like when it is given unobstructed access to the surface, and the most dramatic demonstration available to a non-specialist observer of the geological forces that have shaped the planet throughout its history. The island is geologically young by any standard. The oldest rocks exposed at its surface are approximately 16 million years old, the equivalent of a geological eye blink on a planet whose history extends 4.5 billion years. And it is still growing, new lava adding to its area with every eruption, while the tectonic spreading of the mid-Atlantic ridge slowly pulls its eastern and western halves apart at a rate of approximately 2.5 centimeters per year. The visible expression in the landscape of the same process that created the Atlantic Ocean over the past 200 million years. Iceland's volcanic history in the period of human settlement, beginning with the Norse arrival in approximately 874 CE, is one of almost continuous eruption. The island has experienced eruptions from at least 30 of its volcanic systems in that time, including the catastrophic Laki eruption of 1783 to 1784, in which a fissure eruption of extraordinary volume released 14 cubic kilometers of basaltic lava and a sulfur dioxide cloud whose specific consequences, crop failures across Europe, famine in Iceland that killed a quarter of the island's population, and a climatic disruption that may have contributed to the drought that helped trigger the French Revolution, demonstrated with terrible clarity that the consequences of major volcanic eruptions extend far beyond the immediate vicinity of the erupting vent. Fact 9. Yellowstone, the supervolcano beneath America. Beneath the geysers and hot springs and fumaroles of Yellowstone National Park in Wyoming, beneath the remarkable landscape of boiling mud pools, rainbow-colored thermophilic bacterial mats, and the erupting water columns of Old Faithful and its companions that draw millions of visitors each year to one of the most geologically active landscapes in the United States, lies one of the largest and most powerful volcanic systems on Earth. A magma chamber of extraordinary dimensions, fed by a mantle plume that has been burning through the North American plate for at least 17 million years, and capable, on the evidence of its geological record, of eruptions whose scale and consequences would dwarf anything in the historical record of human civilization, and reshape the climate and ecology of the entire Northern Hemisphere. Yellowstone is a supervolcano, a volcanic system capable of producing eruptions with an ejecta volume exceeding 1,000 cubic kilometers, a threshold defined not by any single geological feature, but by the specific consequences of an eruption at that scale. The collapse of a caldera rather than the construction of a cone, the distribution of ash across continental distances, and the injection of sufficient sulfur dioxide into the stratosphere to produce a volcanic winter of sufficient duration and severity to cause widespread crop failures and significant global temperature reduction. The Yellowstone system has produced 3 supervolcanic eruptions in its documented geological history. The Huckleberry Ridge eruption approximately 2.1 million years ago, which ejected approximately 2,500 cubic kilometers of material. The Mesa Falls eruption approximately 1.3 million years ago. And the Lava Creek eruption approximately 640,000 years ago, which produced the 45 by 85 kilometer caldera that underlies much of the modern national park. The apparent interval between these eruptions, roughly 600,000 to 800,000 years, combined with the 640,000 years that have passed since the last one, has generated considerable popular anxiety about whether Yellowstone is overdue for another supervolcanic eruption. The scientific consensus is that the system's behavior does not follow a regular cyclical pattern, and that the specific magma conditions required for another supereruption are not currently present beneath the park. But the consensus also acknowledges that the monitoring of Yellowstone, however sophisticated, represents a very short window of observation into a geological system of incomprehensible timescale. Fact 10: the volcanoes at 10, a planet alive. 10 facts into the story of the volcanoes, and already the scale of what we are describing has begun to resist the ordinary categories of comprehension. We have stood at the conceptual opening of the Earth and understood that a volcano is not a feature of the planet's surface, but a function of its interior. One of the primary mechanisms by which a world 4.5 billion years old continues to cycle its material, release its heat, and reshape the surface on which everything that has ever lived has made its home. We have followed the map of tectonic plates and understood why the Ring of Fire encircles the Pacific in a horseshoe of 450 volcanic systems, why Iceland grows by centimeters each year from a crack in the ocean floor, why the islands of Hawaii are the surface expression of a mantle plume that has been burning through the Pacific plate for 70 million years. We have stood in the buried streets of Pompeii and understood what it means for a volcano to reach into a human civilization and stop it, completely and permanently, in a single morning. We have heard, across 4,800 kilometers of ocean, the sound that Krakatau made when it tore itself apart in 1883. And we have stood at the rim of Yellowstone and looked down into a landscape of boiling water and colored bacteria, and understood that beneath our feet lies a magma chamber of sufficient size and sufficient heat to reshape the climate of a hemisphere. 90 facts remain. They will carry us through the most dramatic eruptions in the geological record, through the volcanoes of other worlds, through the specific human stories of people who have lived in the shadow of volcanic mountains for generations, and through the deep question of what the Earth's interior is still preparing for the surface above it. The fires beneath the world have not finished their work. This is explored during sleeping. Fact 11. Mount St. Helens, the day a mountain disappeared. The eruption of Mount St. Helens in Washington State on the morning of May 18, 1980, the most destructive volcanic event in the recorded history of the contiguous United States, in which a magnitude 5.1 earthquake triggered the largest landslide in recorded history, removing the entire northern face of the volcano in a matter of seconds, and exposing the pressurized magma chamber beneath to a lateral blast of superheated gas and rock that devastated an area of approximately 600 square kilometers of forest, killed 57 people, and reduced the mountain's summit elevation from 2,950 meters to 2,549 meters in less than 2 minutes. Was the event that transformed American public understanding of volcanic hazard from an abstract geological concept into a visceral national experience, and the event that more than any other shaped the development of modern volcanological monitoring techniques in the United States. The eruption had been anticipated for weeks. Beginning in March 1980, a series of earthquakes and small steam explosions had indicated that magma was moving into the volcanic system, and the bulge that began growing on the volcano's north flank at a rate of up to 2 meters per day, the visible surface expression of a cryptodome of magma intruding into the mountain's interior, was monitored with increasing alarm by United States Geological Survey volcanologists, who correctly identified it as a sign of imminent major activity. The evacuation of residents from the immediate vicinity of the mountain had been ordered, but the specific direction of the eruption's energy, not upward, as a conventional Plinian column, but laterally northward, in a directed blast whose specific character had not been fully anticipated, caught several people who had believed themselves to be at a safe distance. Among those killed was the volcanologist David Johnston, who died at his monitoring station 8 kilometers north of the summit. His last radio transmission, "Vancouver, Vancouver, this is it," becoming one of the most quoted final words in the history of American science. The landscape created by the eruption, the vast grey debris field. The flattened forest of silver tree trunks pointing away from the blast like compass needles, the new lava dome growing within the crater, became one of the most studied volcanic landscapes in the world. a natural laboratory for the understanding of both volcanic processes and ecological recovery, whose lessons continue to inform volcanology decades later. Fact 12. The Volcanic Explosivity Index, measuring the unimaginable. The Volcanic Explosivity Index, the logarithmic scale developed by volcanologists Chris Newhall and Stephen Self in 1982 to provide a standardized, comparative measure of the size and intensity of volcanic eruptions, running from 0 for the smallest effusive eruptions to 8 for the largest supervolcanic events in the geological record, and structured on the same logarithmic principle as the Richter scale for earthquakes. Meaning that each step up the scale represents an eruption approximately 10 times larger in volume than the one below it, is the primary tool by which volcanologists communicate the scale of volcanic events across the full range of volcanic behavior, from the gentle lava flows of Kilauea, which typically register at VEI 0 or 1, to the supervolcanic eruptions of Yellowstone and Tambora, which register at VEI 8 and represent a category of geological event for which no direct human observational record exists. The practical consequence of the logarithmic structure of the VEI is that the difference in scale between events at opposite ends of the index is genuinely difficult to visualize in intuitive terms. A VEI 8 eruption ejects more than 1,000 cubic kilometers of material, a volume sufficient to bury the entire land area of South Africa under a meter of ash, or to cover the continental United States in a layer of volcanic debris deep enough to collapse most structures. The largest eruption in the historical record, Tambora in 1815, which will be discussed in a subsequent fact, registered at VEI 7, ejecting approximately 160 cubic kilometers of material. The 1980 eruption of Mount St. Helens, catastrophic as it was in human terms, registered at VEI 5, 100 times smaller than Tambora in terms of ejected volume. The eruption of Vesuvius that buried Pompeii registered at VEI 5. The 1991 eruption of Mount Pinatubo, the second largest eruption of the 20th century, registered at VEI 6. The last VEI 8 eruption on Earth occurred approximately 26,500 years ago at the Taupo volcanic zone in New Zealand. The geological record contains evidence of VEI 8 eruptions occurring at intervals of hundreds of thousands of years throughout the planet's history, each one a reminder that the volcanic systems currently monitored by the most sophisticated geophysical instruments available to modern science represent only a fraction of the total volcanic energy the Earth is capable of releasing. Fact 13. Tambora, the eruption that changed the world's weather. The eruption of Mount Tambora on the island of Sumbawa in the Dutch East Indies, now Indonesia, between April 5 and April 15, 1815, was the largest volcanic eruption in the entire historical record. A VEI 7 event that ejected approximately 160 cubic kilometers of material, killed an estimated 71,000 people in the immediate vicinity through pyroclastic flows, tsunamis, and the famine and disease that followed the destruction of the island's agriculture, and injected into the stratosphere a sufficiently large quantity of sulfur dioxide to produce the most severe short-term climate disruption of the entire modern period. A global cooling event whose specific consequences were felt on every inhabited continent and whose most famous manifestation was the year 1816, which entered the historical record as the year without a summer. The specific mechanism by which Tambora's eruption affected global climate was the conversion of its stratospheric sulfur dioxide emissions into sulfate aerosols, tiny reflective particles that spread through the upper atmosphere over the months following the eruption and reduced the amount of solar radiation reaching the Earth's surface by a measurable percentage. Resulting temperature reductions, averaging approximately 0.4 to 0.7 degrees Celsius globally, but significantly larger in specific regions, was sufficient to cause catastrophic disruptions to agricultural systems across the Northern Hemisphere in 1816. In New England and Canada, frosts occurred in every month of the year. In Europe, crop failures produced famine conditions across large parts of France, Germany, Switzerland, and the British Isles. In China, the monsoon patterns were disrupted, producing floods in some regions and drought in others. The specific cultural consequences of the year without a summer include, among many other things, the composition of Mary Shelley's Frankenstein, written during the cold, dark, storm-ridden summer of 1816 that kept Shelley, Percy Shelley, Lord Byron, and John Polidori confined indoors at the Villa Diodati near Lake Geneva, where Byron's suggestion that each member of the party write a ghost story produced two of the foundational texts of modern horror literature. The eruption that no one in Geneva could have known was responsible for their sunless summer gave the world, indirectly, one of its most enduring literary monsters. Fact 14. Hawaii volcanoes at the heart of the Pacific. The Hawaiian Islands, the chain of volcanic islands and seamounts stretching approximately 2,400 kilometers across the central Pacific Ocean, from the geologically oldest and most eroded islands in the northwest to the geologically youngest and most volcanically active in the southeast. Created by the movement of the Pacific Plate over a fixed mantle hotspot, whose specific location beneath the ocean floor has remained approximately stationary for at least 80 million years, while the plate above it has moved steadily to the northwest at a rate of approximately 9 centimeters per year, represent one of the most complete and most visually accessible demonstrations anywhere on Earth of the relationship between plate motion, mantle plume activity, and the creation of volcanic island chains over geological time. The specific mechanism of Hawaiian volcanism is the mantle plume, an unusually hot column of mantle material rising from deep within the Earth, possibly from the boundary between the mantle and the outer core, that melts the base of the Pacific Plate as it passes overhead, producing basaltic magma that rises through the plate to erupt on the ocean floor. As the Pacific Plate moves to the northwest, each volcano that has formed over the hotspot is carried away from the heat source, its eruptions gradually diminishing as its magma supply is cut off, while a new volcano begins forming on the ocean floor above the hotspot to the southeast. The result, over 80 million years, is the Hawaiian Emperor Seamount Chain, a geological record of the Pacific Plate's motion preserved in a line of volcanic islands and submerged seamounts that grows progressively older to the northwest, the oldest seamounts of the chains far in dating to approximately 80 million years ago, the youngest island, the Big Island of Hawaii, still actively growing from the eruptions of Kilauea and Mauna Loa. Kilauea, on the Big Island's southeastern flank, is one of the most continuously active volcanoes on Earth, erupting almost without interruption between 1983 and 2018, adding new land to the island's southeastern shore with every lava flow that reached the sea and hissed into existence a new frontier of the Hawaiian Islands. The specific beauty of Hawaiian volcanic landscapes, the black lava fields, the lava tubes, the steam plumes where lava meets ocean, the new black sand beaches created by the cooling and fragmenting of lava in the surf, draws visitors from across the world to stand at the edge of a geological process that is, in the most literal sense, creating new land in real time. Fact 15. Pyroclastic flows, the most dangerous thing a volcano can produce. Of all the phenomena that a volcanic eruption can generate, lava flows, ash falls, volcanic gases, lahars, tsunamis, volcanic bombs, the pyroclastic flow is widely regarded by volcanologists as the most immediately and most comprehensively deadly. A phenomenon of such extreme temperature, such extreme velocity, and such extreme destructive capacity that no structure built by human hands and no speed achievable by a human being on foot can provide reliable protection against it, and whose specific character, the combination of superheated gas, ash, and rock fragments moving as a single coherent mass at temperatures between 200 and 700 degrees Celsius and velocities between 100 and 700 kilometers per hour, makes it one of the most terrifying phenomena in the natural world. A pyroclastic flow forms when the eruption column of a volcano, the rising column of gas, ash, and rock that an explosive eruption drives upward into the atmosphere, becomes too dense and too heavy to continue rising and collapses back to Earth, the collapsing material becoming the fast-moving avalanche of hot gas and debris that sweeps down the volcano's flanks and across the surrounding landscape, filling valleys, crossing ridges, and destroying everything in its path with a thoroughness that leaves, in the geological record, a distinctive deposit called ignimbrite, whose specific texture and composition allow volcanologists to identify and date ancient pyroclastic flows millions of years after the eruptions that produced them. The specific lethality of pyroclastic flows in the historical record is illustrated most vividly by the eruption of Mount Pelée on the Caribbean island of Martinique on May 8, 1902, a pyroclastic surge that descended from the volcano's summit and swept through the port town of Saint-Pierre in less than 2 minutes, killing approximately 30,000 people and leaving, according to the initial reports, only 2 survivors in the town itself. One of those survivors was a prisoner named Ludger Silbaris, confined in a partially underground stone cell whose specific construction, thick walls, a heavy door, a ventilation slot facing away from the volcano, provided just sufficient insulation against the surge's heat to allow him to survive with severe burns. He was discovered days later and eventually pardoned, going on to spend years touring with Barnum and Bailey's circus as the man who survived the destruction of Saint-Pierre. Fact 16. Volcanic winter, when eruptions change the climate. The specific phenomenon of volcanic winter, the measurable, sustained reduction in global surface temperatures caused by the injection of large quantities of sulfur, dioxide into the stratosphere during major volcanic eruptions, where the gas is converted into sulfate aerosols that reflect incoming solar radiation back into space before it can warm the Earth's surface, is one of the most consequential and most historically significant of all volcanic effects. Representing the mechanism by which individual geological events of sufficient magnitude have repeatedly disrupted the climate, agriculture, and political stability of human civilizations across the full span of recorded history and deep into the prehistoric past. The sulfate aerosols produced by major eruptions are not distributed locally or even regionally, but globally, carried by stratospheric winds around the entire planet within weeks of an eruption, creating a reflective veil that reduces solar radiation, reaching the surface by between 1 and 10% depending on the eruption scale, and persisting in the stratosphere for between 1 and several years before gradually settling out. The climate cooling produced by this mechanism is superimposed on whatever background climate trend is already underway, amplifying cold periods and temporarily offsetting warming trends in ways that can produce, at the local and regional level, temperature anomalies of sufficient magnitude to cause harvest failures. The historical record contains numerous examples of volcanic eruptions whose climatic consequences can be traced in the agricultural, political, and social records of the societies they affected. The eruption of an unidentified volcano in 536 CE, whose specific identity has been debated by volcanologists, with candidates in Iceland and El Salvador, produced a dust veil that dimmed the sun across the northern hemisphere for 18 months. Initiating what climate historians have called the late antique Little Ice Age, and contributing to the social and political disruptions of the following decade that accelerated the decline of the late Roman and Sasanian Persian empires. The eruption of Samalas in Indonesia in 1257 CE produced the largest sulfate aerosol injection of the past 7,000 years, cooling the northern hemisphere sufficiently to contribute to the crop failures and famine of the early 1260s. The specific relationship between volcanic eruptions and historical catastrophe, the frequency with which major social disruptions in the written record cluster around the dates of large eruptions, identified in the ice core record, is one of the most active and most productive areas of current historical and volcanological research. Fact 17. Etna, Europe's largest and most active volcano. Mount Etna, the massive stratovolcano on the eastern coast of Sicily, whose summit elevation of approximately 3,350 meters makes it the highest active volcano in Europe, whose documented eruption history extends back at least 2,500 years to the records of ancient Greek colonists who settled on the fertile volcanic soils of its lower slopes and regarded its periodic eruptions with a mixture of agricultural gratitude and religious awe, and whose specific activity patterned near-continuous low-level eruption from its summit craters, punctuated by periodic larger flank eruptions that have threatened the surrounding towns and cities with lava flows and volcanic ash falls, has made it the most studied and most continuously monitored volcano in the world. Occupies a unique position in the cultural and geological history of Mediterranean civilization as the volcano that has been present and active throughout the entire span of recorded Western history, a permanent feature of the Sicilian landscape, whose specific behavior has shaped the experience of every civilization that has lived within its shadow. The ancient Greeks who colonized Sicily in the 8th and 7th centuries BCE built their cities within sight of Etna's smoke and incorporated the volcano into their mythology with the specific creativity that characterized their approach to natural phenomena. The forge of Hephaestus, the god of fire and the craft of metalworking, was located beneath its summit. The giant Typhon, the last great monster of the primordial world, was imprisoned beneath the mountain, his struggling responsible for its earthquakes and eruptions. And the philosopher Empedocles, according to a tradition of uncertain reliability but enduring appeal, leaped into Etna's crater in approximately 430 BCE in an attempt to prove his divinity, his iron sandals ejected by the volcano, providing the only evidence of his fate. The fertility of the volcanic soils on Etna's lower slopes, enriched by millennia of ash deposits, whose specific mineral composition supports an agricultural productivity unusual in the Mediterranean, has ensured that human settlements have persisted in the volcano's immediate vicinity throughout its entire documented history, accepting the periodic risk of lava flows and ash falls as the price of the agricultural abundance the volcano's periodic eruptions have always, over the long run, provided. Fact 18. Underwater volcanoes, the eruptions nobody sees. The overwhelming majority of the world's volcanic activity occurs not on land, where it is visible, documented, and experienced by human populations, but beneath the oceans, At the mid-ocean ridges where tectonic plates are pulling apart and new seafloor is being continuously created, at subduction zones where the descending plate generates arc volcanism on the ocean floor, and at oceanic hotspots where mantle plumes produce submarine volcanic chains whose surface expression, where it exists at all, is the occasional volcanic island rising above the waves as the exposed summit of a vastly larger underwater volcanic structure. The global mid-ocean ridge system, the continuous underwater mountain chain that runs through every major ocean basin, totaling approximately 65,000 kilometers in length and representing the single largest geological feature on the surface of the Earth, is the site of more volcanic eruptions by number than all of the world's subaerial volcanoes combined. With an estimated 3 cubic kilometers of new ocean crust being created along the ridge system every year through the continuous effusion of basaltic magma from the rift valleys at the ridge crests. The specific character of underwater volcanism at mid-ocean ridges differs fundamentally from the explosive eruptions familiar from land-based volcanoes, primarily because the enormous pressure of the overlying water column suppresses the exsolution of dissolved gases from the magma, preventing the explosive decompression that characterizes subaerial eruptions and instead producing pillow lavas. Characteristic rounded lava structures, whose specific globular form is created by the rapid quenching of the lava's outer surface upon contact with seawater, which solidifies before the interior has stopped flowing and produces the distinctive pillow shapes that cover vast areas of the ocean floor. The hydrothermal vent systems associated with mid-ocean ridge volcanism, the seafloor hot springs where superheated mineral-rich water circulates through the newly formed oceanic crust and emerges at temperatures of up to 400 degrees Celsius, were discovered in 1977 by researchers diving in the submersible Alvin near the Galapagos Rift, and their discovery fundamentally revised the understanding of where life can exist on Earth, demonstrating that entire ecosystems, tube worms, giant clams, shrimp, and the chemosynthetic bacteria on which they feed, can thrive in complete darkness, powered not by sunlight but by the chemical energy of the Earth's interior. Fact 19. The Toba catastrophe, when volcanoes nearly ended us. The eruption of the Toba supervolcano on the island of Sumatra in Indonesia, approximately 74,000 years ago, a VEI-8 event of such extraordinary magnitude that it ejected an estimated 2,800 cubic kilometers of material, the largest known eruption on Earth in the past 2 million years, and produced a volcanic winter of sufficient severity and duration to cause the most extreme climate disruption of the entire Quaternary period, has been the subject of one of the most dramatic and most debated hypotheses in the intersection of geology and human prehistory. The Toba catastrophe theory, first proposed by the geneticist Stanley Ambrose in 1998, which suggests that the volcanic winter produced by the Toba eruption caused a population bottleneck in the human species so severe that the total number of breeding humans alive on Earth in the aftermath of the eruption may have been reduced to somewhere between 3,000 and 10,000 individuals, a genetic narrowing whose specific signature, the theory argues, can be detected in the relative genetic uniformity of the modern human population compared to what would be expected from a species of our age and geographic distribution. The specific evidence for the Toba catastrophe theory includes the sulfate deposits in ice cores from both Greenland and Antarctica that record the eruption's stratospheric aerosol injection, the layer of Toba ash distributed across an area of approximately 6 million square kilometers of South Asia and the Indian Ocean floor, and the genetic data suggesting that modern humans passed through a severe population bottleneck at approximately the right time. The counter-evidence includes archaeological sites in India that appear to show continuous human occupation through the Toba ash layer, suggesting that at least some human populations survived the eruption's immediate aftermath without the catastrophic disruption the theory predicts. The scientific debate about the Toba bottleneck's reality and severity remains genuinely unresolved, but the specific scale of the Toba eruption, whether or not it nearly ended the human story, is not in dispute. It was an event of a magnitude that the human imagination, accustomed to thinking in human timescales and human spatial scales, is genuinely ill-equipped to comprehend. Fact 20. The volcanoes at 20 fire as a force of history. 20 facts into the story of the volcanoes, and the shape of what we are tracing has become clear. This is not merely a story about geology. It is a story about the specific relationship between the interior of the Earth and the civilizations that have built themselves on its surface. A relationship of extraordinary intimacy and extraordinary asymmetry, in which human beings have consistently chosen to live in the shadows of volcanic mountains because the volcanic soils are the most fertile, the volcanic landscapes are the most dramatic, and the human capacity for normalizing risk is, in the face of beauty and abundance, essentially unlimited. We have watched Pompeii stop in a single morning, preserved so completely by the ash that buried it that we can read the graffiti on its walls 2,000 years later. We have heard Krakatau's detonation across 4,800 kilometers of ocean. We have understood that the year without a summer, the cold, dark, crop-failing year of 1816, was the specific consequence of a mountain in Indonesia tearing itself apart the previous April, injecting a reflective veil of sulfate aerosols into a stratosphere that cared nothing for the harvest calendars of New England or the literary plans of a group of English poets confined indoors on the shores of Lake Geneva. We have stood at the rim of Yellowstone and understood that beneath the boiling mud and the geyser steam lies a magma chamber whose contents, if released, would redefine the geography of catastrophe. And we have understood that 74,000 years ago, a volcano in Sumatra may have looked at our species and nearly ended the story before it had properly begun. 80 facts remain. They will carry us deeper into the volcanic record, to the volcanoes of other planets, to the people who have made their lives beside these mountains of fire, to the scientists who have devoted their careers to understanding what the Earth is preparing beneath our feet, and to the deepest question that the volcanic story poses. What does it mean to live on the surface of a planet that is still, after 4.5 billion years, profoundly and magnificently alive? This is explored during sleeping. Fact 21. Volcanoes on other worlds, fire beyond Earth. The volcanic activity that shapes the surface of the Earth is not unique to our planet. It is a fundamental consequence of planetary formation, of the heat generated by the accretion of material, the decay of radioactive elements, and the tidal forces exerted by gravitational interactions, and it has produced volcanic landscapes on worlds across the solar system whose specific character, whose particular scale and geology and chemistry, differ from the volcanism of Earth in ways that illuminate both the universal principles of planetary geology and the specific conditions that make each world distinct. The most dramatic volcanic landscape in the solar system is not on Earth but on Io, the innermost of Jupiter's 4 large Galilean moons, whose surface is the most volcanically active in the known solar system, covered in hundreds of active volcanic centers that continuously resurface the moon with lava flows and sulfur deposits. Driven not by the radioactive decay that powers Earth's volcanism, but by the tidal forces exerted on Io's interior, by the competing gravitational pulls of Jupiter and the other Galilean moons, which flex and distort the moon's interior with sufficient energy to maintain it in a state of near-continuous volcanic activity. The Voyager 1 spacecraft, during its 1979 flyby of the Jovian system, captured the first images of an active extraterrestrial volcano, a plume from the volcanic vent peel, rising approximately 300 kilometers above Io's surface, in what mission scientist Linda Morabito described as one of the most unexpected discoveries of the entire Voyager program. Mars, despite being geologically far less active than Earth in the present era, bears on its surface the largest volcano in the solar system. Olympus Mons, a shield volcano approximately 22 kilometers high and 600 kilometers wide at its base, whose specific dimensions, more than twice the height of Mount Everest above the Martian datum, with a base area larger than the entire state of Arizona, reflect both the low Martian gravity that allowed volcanic structures to grow to greater heights than Earth's gravity permits and the absence of plate tectonics on Mars. Which means that the Martian crust did not move away from its hotspot, allowing Olympus Mons to accumulate material from billions of years of eruptions in a single location, rather than producing a chain of progressively older volcanic islands, as the Hawaiian hotspot has done. Fact 22. Lava tubes, tunnels through the Earth. Lava tubes, the natural tunnels formed within solidified lava flows, when the outer surface of a moving basaltic lava flow cools and hardens into a solid crust, while the still molten lava beneath continues to flow through the interior, eventually draining out to leave a hollow tube, whose specific dimensions range from human-passable tunnels of 1 meter or 2 in diameter to vast cathedral-like chambers tens of meters wide and hundreds of meters long. Are among the most remarkable and most practically significant geological structures produced by volcanic activity, forming wherever fluid basaltic lava flows across relatively flat terrain for sufficient distance and duration to develop an insulating outer shell, and creating in the process underground passages that have served, throughout human history, as refuges, water sources, sacred spaces, and in the modern era, as potential habitats for future human settlements on the Moon and Mars. The specific mechanism of lava tube formation begins when a basaltic lava flow develops a roofed channel, the outer surface of the moving lava cooling rapidly in contact with the air and solidifying into a crust, while the interior remains liquid and continues flowing. Insulated by the solidified outer shell from the heat loss that would otherwise slow and stop it. The result is a thermally efficient conduit that can transport lava for distances of tens of kilometers from its source vent, extending the reach of a volcanic eruption far beyond what an open lava flow could achieve. When the eruption feeding the tube eventually ceases or diminishes, the remaining lava drains out of the interior, leaving the solidified outer shell as a hollow tunnel, sometimes with lava stalactites hanging from the ceiling where molten material dripped before solidifying, sometimes with benches of solidified lava marking the levels at which the flowing lava stood during the tube's active phase, and always with the specific smooth, rounded cross-section that distinguishes a lava tube from a cave formed by any other geological process. The longest known lava tube on Earth is the Kazumura cave system on the Big Island of Hawaii, which extends for approximately 65 kilometers and descends more than a kilometer in elevation, a tunnel through which the volcanic interior of the island once flowed to the sea. Fact 23. The 1991 eruption of Mount Pinatubo, a modern giant wakes. The eruption of Mount Pinatubo on the Philippine island of Luzon, beginning on June 12, 1991, and culminating in the climactic paroxysmal eruption of June 15, the second largest volcanic eruption of the 20th century, a VEI-6 event that ejected approximately 10 cubic kilometers of material, produced pyroclastic flows that devastated an area of more than 400 square kilometers around the volcano, and injected into the stratosphere the largest sulfur dioxide cloud of the modern instrumental record, approximately 20 million metric tons, whose subsequent conversion to sulfate aerosols produced a measurable global temperature reduction of approximately 0.5 degrees Celsius that persisted for nearly 2 years, was also in the history of volcanological practice. One of the most successful examples of volcanic hazard assessment and population evacuation in the modern era, demonstrating what adequate monitoring, clear communication, and decisive action by public authorities can achieve in reducing the human cost of a major eruption. Mount Pinatubo had been dormant for approximately 500 years before its reawakening in April 1991. And the absence of any historical eruption in the living memory of the surrounding population meant that there was no cultural framework among local residents for understanding the specific warning signs that the Philippine Institute of Volcanology and Seismology and the United States Geological Survey volcanologists who assisted them were observing with increasing alarm in the weeks before the climactic eruption. The decision to evacuate approximately 60,000 people from the volcano's immediate vicinity before the June 15 eruption, a decision taken on the basis of monitoring data and hazard assessments rather than the direct experience of an eruption that had not yet occurred, saved an estimated 5,000 to 20,000 lives that would otherwise have been lost to the pyroclastic flows and ash deposits of the climactic phase. The approximately 800 deaths that did result from the eruption occurred primarily among people who had returned to the evacuation zone before the danger had passed, or who were killed not by the eruption's direct volcanic effects, but by the collapse of roofs under the combined weight of wet volcanic ash and the torrential rains of Typhoon Yunya, which made the catastrophic coincidence of arriving at the Philippines on the same day as the climactic eruption. Fact 24. Volcanologists, the scientists who chase eruptions. The scientific study of volcanoes, volcanology, the branch of geology concerned with the understanding of volcanic processes, the monitoring of active volcanic systems, the assessment of volcanic hazards, and the prediction of future eruptions, is a discipline that combines the full range of geoscientific methods, from the geochemical analysis of lava samples to the satellite monitoring of ground deformation. With the specific physical courage required to conduct field observations in environments where the hazards are real, immediate, and sometimes fatal, and whose practitioners have included, throughout the history of the science, individuals of extraordinary dedication whose specific contributions to the understanding of volcanic processes came at significant personal risk, and in several famous cases at the ultimate cost. The modern discipline of volcanology traces its intellectual origins to the observations of Pliny the Younger during the 79 CE eruption of Vesuvius, the letters to Tacitus that constitute the first detailed eyewitness account of a major volcanic eruption in the Western written record, and whose description of his uncle Pliny, the elder's fatal attempt to observe the eruption from close range, established, at the very beginning of the discipline's history, the specific tension between scientific curiosity and personal safety that has characterized volcanology ever since. Pliny the Elder, the great Roman naturalist, sailed toward Vesuvius as it erupted to both observe the phenomenon and rescue friends trapped on the shore, and died on the beach at Stabiae, overcome, his nephew's account suggests, by the volcanic gases and ash that accompanied the eruption's second day. The modern era of volcanology was advanced significantly by the work of scientists who accepted extraordinary levels of personal risk in the pursuit of measurements and observations that could only be obtained in close proximity to active lava flows, erupting vents, and volcanic craters. The French volcanologists Caicher and Maurice Krafft, whose 40-year partnership produced thousands of hours of close-range volcanic film footage, and whose specific contributions to the communication of volcanic hazard to public audiences were directly credited by officials in the Philippines with motivating the evacuation that saved tens of thousands of lives before the Pinatubo eruption, died together on June 3, 1991, on the slopes of Japan's Unzen volcano. Killed by a pyroclastic flow while filming from what they had believed to be a safe observation point, 12 days before the eruption they had helped inspire the evacuation for. Fact 25. The Deccan Traps, when volcanism shaped mass extinction. The Deccan Traps, the vast volcanic province covering approximately 500,000 square kilometers of the western Indian subcontinent, formed between approximately 66 and 68 million years ago by one of the largest volcanic events in the geological record of the past 100 million years, in which a mantle plume, or a series of related volcanic events, produced enormous volumes of flood basalt over a geologically brief period. Building up layers of solidified lava flows that in some areas reach a thickness of more than 2 kilometers, have been at the center of one of the most productive and most contentious debates in modern paleontology and geology. The question of what role, if any, this extraordinary episode of volcanic activity played in the mass extinction event at the end of the Cretaceous period, approximately 66 million years ago, that killed the non-avian dinosaurs, approximately 3/4 of all species then living on Earth, and fundamentally restructured the trajectory of life's evolution on this planet. The dominant explanation for the end Cretaceous mass extinction is the impact of a large asteroid or comet at what is now the Yucatan Peninsula of Mexico, the Chicxulub impactor, whose collision with the Earth produced an impact winter, acid rain, wildfires, and a suite of other environmental disruptions sufficient, in the assessment of most paleontologists, to explain the specific pattern of extinctions in the fossil record. The Deccan Traps volcanism, whose timing overlaps with the Chicxulub impact within the resolution of the geological dating methods available, is believed by most researchers to have contributed to the environmental stress of the extinction event, releasing carbon dioxide, sulfur dioxide, and other volcanic gases that affected global climate and ocean chemistry, though the relative weight of the volcanic and impact contributions to the extinction remains debated. What is not debated is the extraordinary scale of the Deccan volcanism itself, a volcanic event that produced, over its active phase, approximately 1 million cubic kilometers of basaltic lava, reshaping the landscape of what would become the Indian subcontinent, and demonstrating that the Earth's volcanic capacity, on its largest scale, operates at dimensions that dwarf anything in the historical or even the prehistoric human record. Fact 26. Lahars, the deadly rivers of mud. Among the secondary hazards produced by volcanic eruptions, the volcanic phenomena that are not direct products of the eruption itself, but are generated by the interaction of volcanic material with water, snow, ice, or the existing landscape. Lahars occupy a special position of particular danger precisely because of their capacity to travel vast distances from the erupting volcano, to strike areas that may appear geographically safe from the eruption's direct effects, and to do so with a speed and a force that gives the populations in their path very little time to respond. A lahar, the Indonesian word for a volcanic mudflow, adopted as the international technical term because so many historically significant examples have occurred in Indonesia, is a mixture of volcanic material and water, ranging in consistency from a slurry barely thicker than water to a dense, concrete-like flow whose specific density and viscosity allow it to carry enormous boulders, destroy reinforced concrete bridges, and bury entire towns beneath meters of volcanic sediment. The water that triggers lahars can originate from multiple sources: the rapid melting of snow and ice on a volcano's upper slopes by erupted lava or pyroclastic flows, the draining of a summit crater lake, the body of water that accumulates in many volcanic craters, and that represents, when a volcano begins to erupt, an enormous reservoir of lahar-generating water positioned at the highest and most dangerous point of the volcanic edifice. The intense rainfall that frequently accompanies volcanic eruptions, whose ash and aerosol injections into the atmosphere can locally enhance precipitation, or the mixing of volcanic ash deposits with river systems during subsequent rainfall events in the weeks and months following an eruption, generating lahars long after the eruption itself has ended. The The most devastating Laha in the historical record occurred in November 1985, when the eruption of Nevado del Ruiz in Colombia melted the glaciers capping the volcano's summit, generating lahars that descended the river valleys on the volcano's flanks and swept through the town of Amero in the middle of the night with almost no warning. Killing approximately 23,000 of the town's 29,000 residents in what remains the deadliest volcanic disaster of the 20th century. Fact 27. Santorini, the eruption that may have ended a civilization. The catastrophic eruption of the Santorini volcano, the volcanic island in the southern Aegean Sea, known in antiquity as Thera, whose massive caldera-forming eruption in the 2nd millennium BCE was one of the largest volcanic events of the Holocene epoch, ejecting an estimated 60 cubic kilometers of material, generating enormous tsunamis that struck the coastlines of the eastern Mediterranean, and depositing a layer of volcanic ash across a broad swath of the Aegean and eastern Mediterranean, has been the subject of one of the most compelling and most debated hypotheses in the intersection of volcanology and ancient history. The suggestion that this eruption was responsible, directly or indirectly, for the collapse of the Minoan civilization on the island of Crete, the most sophisticated Bronze Age culture of the Aegean world, and possibly the source of Plato's legend of Atlantis, the great civilization that sank beneath the sea in a single catastrophic day and night. The specific date of the Santorini eruption has been contested between archaeologists and scientists using different dating methods, with radiocarbon dating and ice core evidence suggesting a date of approximately 1620 to 1600 BCE, and traditional archaeological chronology placing it closer to 1500 BCE. A discrepancy of more than a century, whose resolution has significant implications for the interpretation of the eruption's relationship to the decline of Minoan civilization. The town of Akrotiri, preserved beneath the volcanic deposits of the Santorini eruption in a state of preservation sometimes compared to Pompeii, its multi-story buildings, its sophisticated drainage systems, its extraordinary fresco paintings of Minoan life, was evacuated before the eruption's climactic phase, as evidenced by the absence of human remains and portable valuables in the archaeological deposits, suggesting that the Akrotiri population received sufficient warning to flee. Where they went and what became of them is one of the most haunting unanswered questions in the archaeology of the Bronze Age Mediterranean. Fact 28. Volcanic gases, the invisible hazard. The gases released by volcanic eruptions, the invisible component of volcanic activity that accompanies every lava flow, every pyroclastic eruption, and every period of volcanic unrest, escaping from the magma as it rises toward the surface and the confining pressure decreases, venting from fumaroles and crater lakes during periods of quiescence, and injected in massive quantities into the atmosphere during major eruptions, are among the most significant and most diverse of all volcanic hazards, capable of killing in the immediate vicinity of an eruption, affecting air quality across regional distances, and altering global climate across timescales of years, yet less visible and less intuitively comprehensible than the dramatic phenomena of lava flows and ash clouds that dominate the popular imagination of volcanic hazard. The dominant gas component of most volcanic emissions is water vapor, steam, constituting between 50 and 90% of the total gas content of most magmas, and responsible for the dramatic white plumes that rise from volcanic vents and are often the most visible sign of a volcano's activity. Carbon dioxide, the second most abundant volcanic gas in most systems, is released both during eruptions and continuously from volcanic fields and degassing magma bodies, and its role in the long-term carbon cycle. Volcanic CO2 emissions being the primary geological source of atmospheric carbon dioxide, balanced over geological time by the weathering of silicate rocks that draws carbon dioxide back out of the atmosphere, makes it a fundamental control on the Earth's long-term climate. The most immediately dangerous volcanic gas to human and animal life is sulfur dioxide, which in sufficient concentrations causes respiratory distress, reacts with water to form sulfuric acid, and whose specific toxic properties have caused fatalities in volcanic areas from the ancient world to the present. Carbon dioxide, heavier than air and therefore capable of accumulating in low-lying areas without warning, was responsible for the most unusual volcanic disaster of the 20th century. The Lake Nyos disaster of August 21, 1986, in which a limnic eruption, the sudden release of carbon dioxide dissolved in the deep water of a volcanic crater lake in Cameroon, released a cloud of CO2 that flowed silently down the surrounding valleys at night, asphyxiating approximately 1,800 people and 3,500 livestock in their sleep. Fact 29. Volcanic islands being born, new land from the sea. Among the most dramatic and most visually compelling manifestations of volcanic activity is the specific phenomenon of a volcanic island emerging from the sea, the process by which submarine volcanism, building up layer upon layer of erupted material on the ocean floor, eventually constructs a volcanic edifice of sufficient height to break the surface of the ocean and announce itself to the world as a new piece of land, raw and black and steaming. In the specific moment when the geological interior of the Earth produces something that was not there before. The birth of volcanic islands has been observed and documented on multiple occasions in the modern era, providing volcanologists with the opportunity to study the specific sequence of events by which a new landmass comes into existence and the specific ecological processes by which life colonizes it. The most famous modern example is the island of Surtsey, the volcanic island that emerged from the North Atlantic approximately 30 kilometers south of Iceland between November 1963 and June 1967, when a submarine eruption on the mid-Atlantic ridge built up a basaltic edifice that eventually broke the surface and continued erupting for 4 years. Creating an island of approximately 2.7 square kilometers at its maximum extent before erosion by the North Atlantic waves began the process of wearing it back down. Surtsey was immediately designated a nature reserve and scientific study area by the Icelandic government, and the subsequent 50 years of ecological monitoring have made it one of the most thoroughly documented examples of primary ecological succession anywhere on Earth, the process by which bare volcanic rock is progressively colonized by bacteria, then mosses, then higher plants, then insects and birds. In a sequence that condenses into decades the ecological development that geological processes normally spread across millions of years. In the Hawaiian Islands, a new seamount called L-O-2BB-IHI is currently building itself on the ocean floor approximately 35 kilometers southeast of the Big Island. Its summit currently approximately 975 meters below the ocean's surface. Its eventual emergence as a new Hawaiian island projected to occur in approximately 10,000 to 100,000 years. Fact 30. The volcanoes at 30, between creation and destruction. 30 facts into the story of the volcanoes, and the paradox at the heart of this subject has become impossible to ignore. That the same geological force that buried Pompeii, killed 30,000 people in St. Pierre in 2 minutes, generated the mudflows that erased the town of Armero in the night, and may have brought the Minoan civilization to its knees, is also the force that built the islands of Hawaii from the ocean floor, that created the fertile soils on which a third of the world's population grows its food, that generated the hydrothermal vents where life may have first emerged on this planet, and that has, over 4.5 billion years, produced every continent, every ocean, and every atmosphere that the Earth has ever possessed. Volcanoes are not malfunctions of a planet that would otherwise be safe. They are expressions of a planet that is alive, that has an interior whose heat and whose motion drive the surface processes on which everything that has ever lived depends. The specific human response to this paradox has been, throughout history, consistent. People have built their homes on volcanic soils, planted their vines on volcanic hillsides, and lived their entire lives within sight of volcanic peaks, because the abundance that volcanic geology provides has always, for most people in most generations, outweighed the risk that the same geology represents. 70 facts remain. They will carry us through the volcanoes that have shaped human history most profoundly, through the extraordinary people who have devoted their lives to understanding these mountains of fire, through the specific beauty that volcanic landscapes possess in a form that no other geological environment can match, and through the question that every person who has ever stood at the rim of an active volcanic crater has eventually asked. What is it that we feel, looking down into the Earth's interior, that we cannot feel anywhere else? This is explored during sleeping. Fact 31. The Laki Eruption, Iceland's catastrophe that shook Europe. The Laki Fissure eruption of 1783 to 1784, the volcanic event that began on June 8, 1783, when a fissure approximately 27 kilometers long opened in the volcanic highlands of southern Iceland and began producing one of the largest basaltic lava eruptions of the past 1,000 years. Continuing with varying intensity for 8 months and releasing approximately 14 cubic kilometers of lava, alongside an estimated 120 million metric tons of sulfur dioxide, was not, in its immediate landscape impact, a dramatic explosive eruption of the kind that produces the iconic imagery of volcanic disaster, but rather a slow, sustained, and in its eventual consequences, profoundly catastrophic outpouring of lava and gas whose specific effects on the atmosphere of the Northern Hemisphere constituted one of the most consequential environmental disasters in the history of European civilization. The sulfur dioxide released by the Laki eruption formed, over the summer and autumn of 1783, a persistent dry fog, the Laki haze that spread across Iceland, Britain, and continental Europe, causing respiratory illness, burning vegetation, and reducing sunlight sufficiently to affect temperatures across the northern hemisphere. In Iceland itself, the consequences were most severe. The fluorine released alongside the sulfur dioxide contaminated the grass and water, killing approximately 60% of the island's livestock and precipitating a famine, the Moðuharðindin, the haze hardships that killed approximately 20% of Iceland's entire population, reducing the island's human numbers to their lowest level since the medieval period. In Europe, the Laki haze contributed to an exceptionally cold winter in 1783 to 1784, one of the coldest in the instrumental record, that produced crop failures across much of the continent, adding to the economic and social pressures that were already, in France, building toward the revolutionary crisis of 1789. The historian John D. Post has argued, in a detailed analysis of the climatic and agricultural consequences of the 1780s, that the Laki eruption and the climatic disruption it contributed to were among the environmental factors that tipped an already stressed French agricultural economy into the specific crisis of bread shortages and rural destitution that provided the material conditions for the French Revolution, making a fissure eruption in an Icelandic highland one of the more improbable contributors to the political transformation of the modern world. Fact 32: Volcanic soil, why people live on volcanoes. The paradox of human settlement in volcanic zones, the consistent historical pattern in which populations have chosen to build their homes, cultivate their fields, and raise their children in the immediate vicinity of active and potentially lethal volcanic mountains, generation after generation, despite the demonstrated capacity of those mountains to produce eruptions of catastrophic destructive power, is not as it might appear from the outside. A simple failure of risk assessment or a cultural expression of fatalistic acceptance, but rather the entirely rational response of agricultural communities to the specific and extraordinary fertility of volcanic soils, whose productivity has, for most people in most generations, provided an abundance so reliable and so superior to any alternative available that the periodic volcanic risk has been accepted as the price of a livelihood that no other landscape could provide. Volcanic soils, formed by the weathering of volcanic rocks and the decomposition of volcanic ash deposits, a process that releases into the soil the specific mineral nutrients that the volcanic material contains in exceptional concentration, are among the most fertile agricultural soils on Earth. The basaltic and andesitic rocks that constitute most volcanic deposits are rich in phosphorus, potassium, calcium, and magnesium, the primary mineral nutrients required by plants, and their relatively rapid weathering rate in humid tropical and subtropical climates releases these nutrients into the soil at rates that sustain agricultural productivity without the artificial fertilization that most other soil types eventually require. The volcanic soils of Java, formed from the weathering of the island's numerous active volcanoes, support, on an island covering approximately 132,000 square kilometers, a human population of approximately 155 million people. A population density made possible almost entirely by the extraordinary agricultural productivity of soils formed from the repeated eruptions of the volcanoes that tower over the rice paddies below. The vineyards of southern Italy, the Campanian wines whose specific character is attributed by their producers to the volcanic soils of the slopes of Vesuvius and the Campi Flegrei, the coffee plantations of Hawaii and Guatemala, the rice terraces of Bali and the Philippines, the wheat fields of the Pacific Northwest. All represent the specific choice, made by millions of people across centuries and cultures, that the fertility of volcanic soil is worth the risk of living within reach of the fire that created it. Fact 33: Stromboli, the lighthouse of the Mediterranean. Stromboli, the small volcanic island in the Tyrrhenian Sea north of Sicily, one of the 7 Aeolian islands whose collective volcanism has shaped the mythology and the geography of the central Mediterranean since antiquity, has been in a state of nearly continuous eruption for at least 2,000 years. Its summit vents producing small to moderate explosive eruptions at intervals of between 15 minutes and several hours, with such clock-like regularity that ancient Mediterranean sailors used its glow as a navigational landmark, giving it the name by which it is known to this day, the Lighthouse of the Mediterranean. The specific eruptive style that characterizes Stromboli, the short, rhythmic bursts of incandescent lava fragments and gas that are ejected from the summit crater with a distinctive popping or booming sound, and then fall back onto the volcano's upper slopes in showers of glowing rock, has given its name to an entire category of volcanic behavior, strombolian eruptions. Defined by volcanologists as eruptions of moderate explosivity, driven by the bursting of large gas bubbles that rise through relatively viscous basaltic magma and reach the surface with sufficient force to throw lava fragments to heights of hundreds of meters, but insufficient force to sustain a continuous eruption column. The specific mechanism that makes Stromboli's activity so persistent and so regular has been studied by volcanologists using instruments lowered into the volcanic conduit and seismological networks that monitor the acoustic and seismic signatures of each gas burst, revealing a system in which large slugs of volcanic gas rise slowly through the magma-filled conduit and burst at the surface in a process so consistent in its physics that the interval between eruptions can be predicted with reasonable accuracy from the acoustic signals that precede each burst. Stromboli receives approximately 250,000 visitors each year, many of whom make the 3-hour hike to the summit observation area to watch the eruptions from an authorized viewing distance, making it one of the most visited active volcanoes on Earth and one of the rare geological phenomena that is both genuinely dangerous and genuinely accessible to non-specialist observers. Fact 34. The Campi Flegrei, a supervolcano beneath a city. Beneath the western suburbs of Naples, beneath the apartment buildings and the ancient Roman ruins and the busy harbour of Pozzuoli, beneath the thermal baths and the fumarolic fields, whose sulphurous steam has been rising from the ground since antiquity, lies one of the most closely monitored and most concerning volcanic systems in Europe. The Campi Flegrei, or Phlegrean Fields, a large volcanic caldera approximately 13 kilometres in diameter, whose specific geological character, a resurgent caldera formed by 2 catastrophic eruptions approximately 39,000 and 15,000 years ago, each of which ejected sufficient material to alter the climate of the northern hemisphere, makes it a potential source of volcanic hazard on a scale that would directly threaten the approximately 1 million people who currently live within its boundaries and the 3 million people of the Greater Naples metropolitan area who live in its shadow. The Campi Flegrei caldera is the product of 2 supervolcanic eruptions whose specific scales dwarf anything in the historical record of European volcanism. The Campanian ignimbrite eruption of approximately 39,000 years ago, which ejected an estimated 300 cubic kilometers of material and distributed ash across an area extending from the western Mediterranean to the Caspian Sea, is the largest eruption in Europe in the past 200,000 years, and has been linked by some researchers to a population decline among Neanderthal populations in Europe that may have contributed to their eventual extinction. The caldera that resulted from these eruptions has been showing signs of renewed unrest in recent decades, a phenomenon called bradisism, the slow uplift and subsidence of the ground surface within the caldera caused by the movement of magmatic fluids and gases in the system below, which has produced measurable ground deformation in the Pozzuoli area since the 1950s, and has been monitored with increasing intensity since a period of significant uplift and seismic activity between 1982 and 1984 caused the precautionary evacuation of approximately 40,000 residents from the most at-risk areas of Pozzuoli. The specific question of when and whether the Campi Flegrei will produce another major eruption is one of the most consequential and most difficult problems in contemporary volcanology. Fact 35. Volcanic lightning, fire and storm united. Among the most visually dramatic and scientifically fascinating phenomena associated with major volcanic eruptions is volcanic lightning, the electrical discharges that form within eruption columns and ash clouds, producing lightning bolts that illuminate the interior of the ash plume with the same brilliant white light as conventional thunderstorm lightning, but in a setting of extraordinary visual intensity. With the dark ash cloud lit simultaneously by the lightning above and the incandescent lava below, creating images of such dramatic power that photographs of volcanic lightning have become among the most widely shared and most recognized images in the entire canon of natural disaster photography. The specific mechanisms that generate volcanic lightning are multiple and interacting, and the relative contribution of each mechanism varies with the specific character of the eruption and the stage of the eruption column's development. The most important mechanism in large explosive eruptions is the fragmentation of magma by the explosive decompression of dissolved gases, the same process that drives the eruption itself, which generates enormous quantities of fine ash particles, whose collisions during the rapid turbulent mixing of the eruption column produce static electrical charge in the same way that the collisions of ice crystals and graupel generate static electricity within conventional thunderstorm clouds. In smaller eruptions and near the vent in larger ones, the triboelectric charging of ash particles against each other and against the volcanic vent walls generates sufficient electrical charge to produce the specific pattern of near-vent lightning that has been observed in high-resolution imagery of eruptions, including the 2010 eruption of Eyjafjallajökull in Iceland. The eruption best known to the general public for the disruption of European air travel, but whose photographic record includes some of the most remarkable volcanic lightning images ever captured. The study of volcanic lightning has practical applications beyond its visual drama. The electromagnetic signals produced by volcanic lightning can be detected at distances of thousands of kilometers from an erupting volcano, providing a potential monitoring tool for eruptions in remote locations where conventional ground-based monitoring networks are absent. Fact 36. The year 536, the worst year in human history. The year 536 CE, identified by the medieval historian and archaeologist Michael McCormick as the beginning of one of the worst periods to be alive, if not the worst year, and characterized in the historical record of the Northern Hemisphere by a persistent atmospheric fog that dimmed the sun across Europe, the Middle East, and parts of Asia for between 18 months and 2 years. Producing the coldest decade in the past 2,300 years, and triggering a sequence of crop failures, famines, social disruptions, and epidemic disease that cumulatively constitutes one of the most severe environmental and human crises of the entire Common Era, began with a volcanic eruption, whose specific source remained unidentified for decades before ice core evidence from both Greenland and Antarctica. Combined with the discovery of volcanic ash in a Greenland ice core dated to 536, pointed to a large eruption in Iceland, or possibly in North America or Central America, as the origin of the atmospheric veil that plunged the Northern Hemisphere into an extended period of cold and darkness. The specific consequences of the 536 event, as recorded in the historical sources of the period, are both consistent and alarming. The Byzantine historian Procopius wrote that the sun gave forth its light without brightness, like the moon, during this whole year. The Italian senator Cassiodorus described a sun whose rays provided no warmth, and a moon that appeared stripped of its natural splendor. And dendrochronological records from tree rings in Europe, Siberia, and North America show the most severe summer cooling in the instrumental record for the first millennium CE, with temperatures in some regions falling by between 1.5 and 2.5 degrees Celsius below the pre-536 baseline. The 536 eruption initiated what climate historians now call the Late Antique Little Ice Age, a period of sustained cooling that persisted, with the additional contribution of 2 further large volcanic eruptions in 540 and 547, until approximately 660 CE, and whose specific climatic consequences have been linked by historians to the outbreak of the plague of Justinian. The disruption of the Sasanian Persian economy, the weakening of the Eastern Roman Empire, and the political transformations across Europe and Asia that reshaped the post-Roman world. Fact 37. Volcanoes and the origin of life, the cradle of creation. The specific relationship between volcanic activity and the origin of life on Earth. The possibility that the chemical and thermal environments created by volcanic systems provided the specific conditions in which the first self-replicating molecules emerged from non-living chemistry, initiating the evolutionary process that would eventually produce every organism that has ever lived on this planet, is one of the most profound and most actively researched questions in the intersection of volcanology, geochemistry, and the science of life's origins, and one that places volcanic activity not merely in the role of a geological hazard or a landscape-forming process, but as a potential fundamental prerequisite for the existence of biology itself. The hypothesis that life originated at hydrothermal vents, the volcanic hot springs on the ocean floor, discovered in 1977, where superheated, mineral-rich water circulates through newly formed oceanic crust and emerges at the seafloor in conditions of high temperature, high pressure, and high chemical energy, was first proposed in its modern form by the oceanographer Jack Corliss in 1979 and has been developed into one of the most detailed and most chemically specific hypotheses for the origin of life currently under investigation. The specific appeal of the hydrothermal vent hypothesis lies in the remarkable coincidence between the chemical conditions at vent systems and the chemical requirements of the earliest life. The temperature gradients that drive chemical reactions, the mineral surfaces that could have catalyzed the formation of complex organic molecules, the hydrogen and carbon dioxide, whose reaction, mediated by iron-sulfur minerals abundant at vent systems, produces organic compounds by a process that bears a striking resemblance to the core metabolic reactions of the most ancient living organisms. An alternative volcanic hypothesis, that life originated not at deep-sea vents, but in shallow volcanic pools or geothermal springs at the surface, environments whose specific character of alternating wet and dry conditions could have concentrated organic molecules and driven the formation of the lipid membranes that enclose living cells, has been associated with the work of the chemist Jack Szostak and the geoscientist Armen Mulkajanian, and is supported by the observation that the iron concentrations inside living cells more closely resemble the chemistry of fresh volcanic spring water than the chemistry of the ocean. Fact 38. Mauna Loa, the largest volcano on Earth. Mauna Loa, the massive shield volcano that forms the southwestern portion of the Big Island of Hawaii, whose summit rises to 4,169 meters above sea level, but whose true height, measured from its base on the Pacific Ocean floor, reaches approximately 9,170 meters, making it the tallest mountain on Earth when measured from base to summit, and whose total volume of approximately 75,000 cubic kilometers makes it the largest volcano on Earth by mass and one of the largest single geological structures anywhere on the surface of the planet, has been erupting repeatedly throughout its approximately 700,000-year history of subaerial existence, with the most recent eruption occurring in November and December of 2022, the first eruption since 1984. And the specific character of its activity, the effusion of highly fluid basaltic lava that flows rapidly across the landscape, building up the broad, gently sloping form of the classic shield volcano, making it one of the most closely monitored and most thoroughly studied volcanoes in the world. The United States Geological Survey's Hawaiian Volcano Observatory, established on the rim of Kilauea caldera in 1912 by the geologist Thomas Jagger, is the oldest continuously operating volcano observatory in the United States and the institution that has produced, over more than a century of continuous monitoring, some of the most detailed and most scientifically productive observational records of volcanic behavior available anywhere in the world. Mauna Loa's eruptions, while rarely producing the explosive pyroclastic activity that characterizes the Ring of Fire's stratovolcanoes, present their own specific hazard in the form of rapidly advancing lava flows, whose speed and volume can threaten communities on the volcano's flanks, with insufficient warning time for comfortable evacuation. The 1950 eruption of Mauna Loa produced lava flows that traveled from the summit to the ocean in approximately 3 hours, a speed of advance that left little time for the communities in the flow's paths, and that demonstrated, with the specific clarity that only a real eruption can provide, the inadequacy of the monitoring and warning systems then in place. The lesson was absorbed, and the subsequent decades of investment in monitoring infrastructure at Mauna Loa and Kilauea have made the Hawaiian volcanic system one of the best understood and most effectively managed volcanic hazard zones in the world. Fact 39. Volcanic art and culture, mountains of the gods. The specific cultural responses that human civilizations have developed to the volcanic landscapes in which they have made their homes, the mythologies, the religious traditions, the artistic representations, and the specific systems of meaning through which human communities have interpreted and incorporated the volcanic phenomena that periodically transformed their world, constitute one of the most revealing windows into the relationship between human culture and the natural environment, demonstrating the specific creativity with which the human mind has always sought to find meaning and order in the most overwhelming expressions of natural power. In ancient Rome, the volcanic fire of Vesuvius and the Phlegraean fields was incorporated into the mythology of Vulcan, the lame god of the forge whose divine workshop beneath the earth explained the specific phenomena of volcanic heat, sulfurous gas, and fiery rock in terms that were entirely coherent within the Roman mythological framework, placing volcanic activity within a divine narrative of craft and creation rather than chaos and destruction. In Japan, Mount Fuji, the nearly perfectly symmetrical stratovolcano that has been sacred in Japanese religious tradition for at least 1,000 years, the subject of thousands of paintings, poems, and literary references, and the specific object of a pilgrimage tradition that at its height in the Edo period drew hundreds of thousands of devotees to its summit each year, embodies a specific Japanese aesthetic response to volcanic beauty whose particular character. The combination of perfect form, dangerous power, and serene remoteness has made it the most recognized natural symbol of Japanese culture in the world. In Hawaii, the volcanic tradition is embodied in the figure of Pele, the Hawaiian goddess of volcanoes, fire, and creation, whose specific mythological home is the Kilauea caldera on the Big Island, and whose creative and destructive power, expressed in the lava flows that both destroy existing land and create new land as they reach the sea, captures with great precision the specific paradox of volcanic activity, that creation and destruction are, at the geological level, the same process. Fact 40, the volcanoes at 40, halfway through the fire. 40 facts into the story of the volcanoes, and we have traveled, in thought and in the specific quality of attention that this subject demands, from the center of the Earth to the surface of other worlds, from the sulfurous fissures of the Icelandic highlands to the perfectly symmetrical summit of Mount Fuji, from the buried streets of Pompeii to the hydrothermal vents where life itself may have first assembled from chemistry and heat, and the specific generosity of the volcanic interior. We have understood that volcanoes killed the residents of Armeiro while they slept, buried Pompeii while its people went about their morning errands, and sent a haze across Europe in 536 CE that dimmed the sun for 18 months and may have helped tip the Roman world into its final crisis. And we have understood that the same volcanoes built the islands of Hawaii from nothing, created the soils that feed a billion people, and may have provided the specific chemical cradle in which the first molecules capable of copying themselves, the first tenuous beginning of what would eventually become all life on Earth, assembled themselves in the hot, dark, mineral-rich water of a seafloor vent 3.5 billion years ago. 60 facts remain. They will carry us through the individual stories that make this subject human, the scientists who have given their lives to understanding these mountains, the communities that have survived their eruptions and returned to rebuild, the specific moments in which volcanic fire has intersected with human history in ways that changed everything. The Earth beneath us is still warm. The fires have not gone out. This is explored during sleeping. Fact 41, Mount Vesuvius today, the most dangerous volcano in Europe. Mount Vesuvius, the stratovolcano on the eastern shore of the Bay of Naples, whose eruption in 79 CE buried Pompeii and Herculaneum, and whose name has been synonymous with volcanic catastrophe in the Western imagination ever since, remains, in the assessment of volcanologists and emergency management authorities, the most dangerous volcano in Europe and one of the most dangerous in the world. Not because of any exceptional geological violence in its recent behavior, but because of the specific combination of its demonstrated capacity for large explosive eruptions and the approximately 3 million people who currently live within the area that would be directly threatened by a major eruption, making the potential human consequences of a significant Vesuvian eruption greater than those of almost any other volcanic scenario in the world outside of the densely populated volcanic zones of Southeast Asia. Vesuvius has erupted more than 50 times since the eruption of 79 CE, with the most recent eruption occurring in 1944, during the Italian campaign of the Second World War, when lava flows and ash falls destroyed several aircraft of the United States Army Air Forces stationed at Pompeii Airfield and caused the evacuation of the towns of San Sebastiano al Vesuvio and Massa di Somma. An event that was simultaneously a significant volcanic episode and a minor footnote in the vastly larger catastrophe of the war then consuming Italy. Since 1944, Vesuvius has been quiescent, its summit crater producing only minor fumarolic activity, but the monitoring systems maintained by the Osservatorio Vesuviano, the oldest volcano observatory in the world, established in 1841 on the volcano's slopes, detect the continued presence of a magma system at depth and a level of background seismic and hydrothermal activity consistent with a volcano that is dormant rather than extinct. The Italian government's emergency plan for a major Vesuvius eruption, the Piano Nazionale di Emergenza per il Vesuvio, identifies a red zone of approximately 200,000 people requiring evacuation before any major eruption, a process estimated to require at least 1 week of continuous organized movement and representing one of the most logistically complex peacetime emergency planning challenges in Europe. Fact 42, volcanoes and tsunamis, when fire meets the ocean. The relationship between volcanic activity and tsunami generation, the specific mechanisms by which volcanic events, at or near the ocean, can displace sufficient volumes of water to produce the devastating waves that travel across ocean basins at the speed of a commercial aircraft and arrive at distant coastlines with heights and energies capable of destroying coastal communities, is one of the most important and most complex aspects of volcanic hazard assessment in the modern era. Encompassing several distinct physical processes whose relative contributions to specific historical tsunami events have been the subject of considerable scientific debate and whose understanding has been substantially advanced by the specific disasters of recent decades. The most straightforward mechanism of volcanic tsunami generation, is the direct displacement of ocean water by the collapse of volcanic edifices into the sea, the process that produced the devastating tsunami of the 1883 Krakatau eruption, in which the collapse of the northern portion of the volcanic island generated waves, estimated at up to 37 meters in height, that killed approximately 36,000 people on the coastlines of Java and Sumatra. A similar mechanism was responsible for the tsunami generated by the December 2018 collapse of the Anak Krakatau volcano. A partial flank collapsed during an eruption that sent a significant portion of the island's southwestern face into the Sunda Strait, generating a tsunami that struck the coastlines of Java and Sumatra without warning, killing more than 400 people and injuring thousands more. At a time when the monitoring systems in place were focused on seismic tsunami warning, detecting tsunamis generated by earthquakes, rather than the non-seismic collapse event that actually triggered the waves. The 2022 eruption of the Tonga Hapai submarine volcano in the Pacific archipelago of Tonga demonstrated a third mechanism: the generation of tsunamis by the atmospheric pressure waves produced by an extraordinarily violent explosive eruption, whose specific shock waves propagated across the Pacific at the speed of sound and produced measurable sea level changes on coastlines as far away as the Mediterranean and the Caribbean. Fact 43: the 2010 Eyjafjallajökull eruption, when a volcano stopped the world. The eruption of Eyjafjallajökull, the stratovolcano on the southern coast of Iceland, whose name became briefly and improbably famous across the world in April 2010, when the ash cloud produced by its subglacial eruption drifted eastward across Europe and triggered the most extensive closure of European airspace since the Second World War, was, by the standards of Icelandic volcanic history, a modest event. A VEI-4 eruption that ejected less than a cubic kilometre of material and caused no direct fatalities, whose specific claim to historical significance lay not in its geological scale, but in the remarkable demonstration it provided of the specific vulnerability of modern globalized civilization to the disruption of air travel, and of the specific gap that existed at the time of the eruption between the scientific understanding of volcanic ash, hazard to jet engines, and the regulatory frameworks within which European aviation authorities were required to make decisions. The eruption began on March 20, 2010 with an effusive phase at the volcano's eastern flank, producing lava flows that attracted tourists and generated little disruption, before migrating to the summit crater in mid-April and encountering the glacier that capped the volcano, whose meltwater poured into the erupting vent and interacted with the magma in a process called phreatomagmatic fragmentation that shattered the lava into extremely fine ash particles of the specific size and density most hazardous to jet engine turbine blades. The resulting ash cloud, carried by the prevailing winds directly across the busiest airspace in the world, caused the cancellation of approximately 100,000 flights over a period of 6 days, stranding approximately 10 million passengers at airports across the world, and costing the aviation industry an estimated $1.3 billion. All as a consequence of a relatively small eruption from a volcano most Europeans could not have located on a map 1 week before it became, briefly and memorably, the most discussed geological feature on the planet. Fact 44: flood basalts when the Earth bled. Flood basalts, the geological formations produced by the most voluminous volcanic events in the Earth's history, in which enormous quantities of highly fluid basaltic lava erupted from fissures or volcanic centers over geologically brief periods, flooding vast areas of the continental or oceanic surface with layer upon layer of solidified lava to depths of hundreds or even thousands of meters, and whose preserved remnants, the large igneous provinces or lips, that are distributed across the geological record of every continent, represent the physical evidence of volcanic events whose scale and duration dwarf anything in the historical or even the recent prehistoric record, are the largest volcanic structures on Earth and the geological expressions of the most extreme volcanic activity the planet has produced since the end of the heavy bombardment of the early solar system. The largest flood basalt province on Earth is the Siberian Traps, the vast accumulation of basaltic lava covering approximately 7 million square kilometers of Siberia, erupted between approximately 251 and 252 million years ago, at the boundary between the Permian and Triassic geological periods. In a volcanic event whose duration was perhaps 1 million years, but whose climactic phase may have lasted only a few tens of thousands of years, and released approximately 4 million cubic kilometers of basaltic magma. The Siberian Traps eruption is strongly associated by geologists with the end Permian mass extinction, the largest extinction event in the history of multicellular life on Earth, in which approximately 90 to 96% of all marine species and approximately 70% of terrestrial vertebrate species were eliminated, through the specific mechanism of the enormous quantities of carbon dioxide, sulfur dioxide, and other volcanic gases released by the eruption, which would have produced both a runaway greenhouse warming effect and the specific ocean acidification, whose consequences for marine calcifying organisms, corals, shellfish, foraminifera, are recorded with terrible completeness in the fossil record of the Permian-Triassic boundary. The specific relationship between large igneous province volcanism and mass extinction events, the repeated coincidence in the geological record between the timing of lip eruptions and the timing of extinction events, is one of the most provocative and most actively researched patterns in the entire history of the Earth sciences. Fact 45. Volcanic monitoring, listening to the Earth. The specific challenge of volcanic monitoring, the scientific and technological effort to detect, measure, and interpret the signals that an active or potentially active volcanic system produces before, during, and after eruptions, with the specific goal of providing sufficient warning of major eruptions to allow the evacuation of threatened populations and the implementation of emergency response measures, has driven, over the past century, the development of a remarkably diverse and sophisticated array of geophysical and geochemical instruments and techniques whose combined application to the world's most hazardous volcanic systems represents one of the most consequential practical applications of Earth science knowledge in the modern era. The earliest systematic volcanic monitoring efforts, the establishment of permanent observatory stations on the flanks of active volcanoes, beginning with the Osservatorio Vesuviano in 1841 and the Hawaiian Volcano Observatory in 1912, were based primarily on the direct visual observation of volcanic activity, supplemented by seismological measurements. The detection of the specific patterns of earthquake activity that accompany the movement of magma through the crust, providing the primary instrumental indicator of impending eruptions. Modern volcanic monitoring systems incorporate a vastly larger array of measurement techniques, including seismic networks that detect and characterize the full spectrum of seismic signals associated with volcanic activity, from the high-frequency earthquakes produced by rock fracturing to the low-frequency tremors associated with fluid movement. Ground deformation monitoring using GPS receivers, tiltmeters, and satellite-based radar interferometry that measures the swelling and subsidence of the ground surface as magma accumulates in or withdraws from the chambers and conduits below. Gas monitoring systems that measure the output of sulfur dioxide, carbon dioxide, and other volcanic gases from the surface, providing information about the depth and rate of magma degassing. And thermal imaging systems that detect changes in the surface heat output of volcanic areas that precede eruptions. The integration of all these monitoring streams into coherent real-time assessments of volcanic hazard, the specific scientific and communicative challenge of translating continuous streams of geophysical data into actionable warnings for civil protection authorities, remains one of the most difficult and most important problems in applied volcanology. Fact 46. The Volcanic Seven Summits, Climbing the Fire Mountains. Among the most dramatic expressions of the human relationship with volcanic mountains is the specific tradition of mountaineering on active volcanoes. The ascent of volcanic peaks not merely as geological field sites or religious pilgrimages, but as athletic and adventurous undertakings, whose particular appeal combines the physical challenge of high-altitude climbing with the unique sensory experience of a mountain that is simultaneously a geological hazard, a landscape of extraordinary beauty, and a direct connection to the interior of the Earth that is available at no other accessible location. The highest active volcano on Earth is Ojos del Salado on the border between Chile and Argentina, whose summit reaches 6,893 meters above sea level, though its last confirmed eruption was in approximately 700 CE, making its status as an active rather than dormant volcano a matter of definitional convention. The highest currently active stratovolcano is Mount Erebus in Antarctica, whose summit elevation of 3,794 meters conceals a persistent lava lake in its summit crater, one of only 5 persistent lava lakes known to exist on Earth, that has been continuously active since its discovery by the members of Ernest Shackleton's 1908 Antarctic expedition. The ascent of active volcanoes has produced some of the most remarkable and most dangerous episodes in the history of mountaineering, including the descent into the active summit crater of Nyiragongo in the Democratic Republic of Congo, a volcano whose lava lake, the largest in the world, sits within a crater accessible on foot and has been visited by volcanologists and adventurers willing to accept the specific risks of descending into a volcanic system, whose history includes two catastrophic lava lake drainage events in 1977 and 2002, in which the rapid outpouring of lava from the crater killed hundreds of people in the communities on the volcano's flanks. Fact 47. Volcanic eruptions and human migration, fire that moved peoples. The specific relationship between major volcanic eruptions and human migration, the evidence, accumulating from archaeology, genetics, and historical records, that volcanic events of sufficient magnitude have repeatedly disrupted the populations in their paths sufficiently to drive significant movements of people across the landscape, contributing to the specific patterns of human dispersal and population replacement that have shaped the genetic and cultural map of the modern world, is one of the most intriguing and most actively investigated questions in the intersection of volcanology and human prehistory. The Tambora eruption of 74,000 years ago, whose potential role as a trigger for a human population bottleneck was discussed in an earlier fact, represents the most extreme proposed example of volcanic disruption of human demography, a single event of sufficient magnitude to have reduced the human species to a few thousand individuals and fundamentally reset the trajectory of human genetic diversity. The archaeological evidence for volcanic disruption of specific human populations in the more recent prehistoric and historical record is more numerous and more firmly established, including the depopulation of large areas of southern Iceland following the Laki eruption of 1783, the abandonment of settlements across the Pacific Northwest following major eruptions of cascade volcanoes in the prehistoric period, and the displacement of populations across Southeast Asia following major Indonesian eruptions that are recorded in both the archaeological and the genetic record of the region. The specific contribution of volcanic events to the larger patterns of human migration that have shaped the modern world, the movements of people out of Africa, the peopling of the Americas, the population replacements of prehistoric Europe, is a subject of active and productive research whose specific conclusions are still being worked out, but whose general finding that volcanic eruptions have been, throughout human history, significant drivers of population movement and demographic change, is increasingly well supported by the convergence of evidence from multiple scientific disciplines. Fact 48. The beauty of volcanic landscapes, geology as aesthetic experience. The specific aesthetic experience of volcanic landscapes, the particular quality of beauty that geothermal fields, lava flows, volcanic craters, and the extraordinary geological formations produced by volcanic processes possess, and that distinguishes them from every other category of natural landscape, has been recognized and described by travelers, artists, scientists, and ordinary observers across the full span of recorded human history, and constitutes one of the most powerful and most distinctive experiences available to anyone who has stood at the rim of an active crater, walked across a fresh lava field, or descended into the steam and color of a geothermal basin. The beauty of volcanic landscapes is inseparable from their geological character, from the specific fact that what the eye is seeing is the Earth's interior made visible, the deep material of the planet exposed at the surface in forms and colors that exist nowhere else in the natural world. The obsidian black of fresh basaltic lava, so smooth and so reflective that the sky is visible in its surface, against the white of steam plumes rising from lava tubes and ocean entry points. The extraordinary palette of Yellowstone's grand prismatic spring, its concentric rings of thermophilic bacteria producing colors from deep blue at the center through green, yellow, and orange to the rust red of the outer edges, the entire spectrum arranged by temperature in a natural illustration of the relationship between heat and life, the lava lakes of Nyiragongo and Erebus. Their surfaces of dark solidified crust, broken by the brilliant orange red of the molten rock below, moving with a slow, viscous deliberateness that makes time itself seem to operate at a different rate. These are visual experiences of a category that no other natural environment provides, and that have been sought by painters, photographers, writers, and explorers with a consistency across cultures and centuries that speaks to something fundamental in the human response to the Earth's interior made visible. The Japanese landscape painter Katsushika Hokusai spent decades of his career depicting Mount Fuji from every conceivable angle and in every conceivable condition of light, producing in his 36 views of Mount Fuji a body of work whose specific aesthetic achievement, the rendering of a volcanic mountain as the organizing principle of an entire civilization's relationship with its landscape, has no precise equivalent in any other artistic tradition. Fact 49. Geothermal energy, harnessing volcanic power. Specific application of volcanic heat to the generation of electrical power and the direct heating of buildings and water, geothermal energy, the exploitation of the thermal energy stored in the Earth's interior that volcanic and tectonic activity brings to or near the surface in concentrations sufficient for practical human use, represents one of the most direct and most sustainable of all the relationships between human civilization and the geological forces of the volcanic Earth, and one whose specific potential contribution to the global energy transition away from fossil fuels has received increasing attention as the scale of the climate challenge has become more clearly understood. Geothermal energy systems exploit the specific fact that in volcanic and tectonically active regions, the temperature of the Earth's crust rises far more rapidly with depth than in geologically stable continental interiors, bringing usable heat to depths accessible by drilling, and in some cases expressing it naturally at the surface in the form of hot springs, geysers, and fumaroles that have been used for heating and cooking by human populations for thousands of years. Iceland is the world's most geothermally dependent nation. Approximately 90% of Icelandic homes are heated by geothermal water, pumped directly from the volcanic aquifers beneath the island, and approximately 30% of the country's electrical power is generated by geothermal power plants, with the remainder supplied almost entirely by hydroelectric power, making Iceland one of the few nations on Earth whose energy supply is effectively 100% renewable. The Hellisheiði power plant near Reykjavik, one of the largest geothermal power plants in the world, not only generates electricity and hot water for the Reykjavik metropolitan area, but also hosts a carbon capture facility that injects captured CO2 into the basaltic rock below, where it mineralizes into solid carbonate within 2 years. Demonstrating the specific potential of volcanic geology not only as an energy source, but as a carbon sequestration medium, whose large-scale application could contribute meaningfully to climate mitigation. Fact 50, the volcanoes at 50, the human scale of an ancient force. 50 facts into the story of the volcanoes, and we have arrived at the midpoint of a journey that began at the center of the Earth and has carried us, fact by fact, through the full range of what the volcanic interior means for the surface on which human beings have built their civilizations and told their stories. We have descended into lava tubes and ascended to the summits of the world's highest volcanic peaks. We have sat at the monitoring stations where scientists watch day and night for the specific signals that might indicate a magma system moving toward the surface. We have stood in the geothermal fields of Iceland and understood that the volcanic heat beneath the ground is simultaneously what makes the island dangerous and what has made it, in the 21st century, one of the most energy-sustainable societies on Earth. We have understood that the same volcanic forces that produced the Permian extinction, the greatest dying in the history of multicellular life, also, over the 4.5 billion years of the Earth's existence, produced the conditions in which life began, and the soils and the climates in which life eventually flourished into the extraordinary diversity that preceded each of those extinctions and has, so far, recovered from all of them. 50 facts remain. They will carry us through the stories that the first 50 have prepared us for the specific eruptions, the specific landscapes, the specific people, and the specific questions about the future of a civilization built on the surface of a volcanically active planet whose interior has not finished reshaping the world above it. The fires continue. This is explored during sleeping. Fact 51. The volcanic arc of Indonesia, the most dangerous archipelago on Earth. Indonesia, the vast archipelago of more than 17,000 islands, stretching approximately 5,100 kilometers from Sumatra in the west to Papua in the east, straddling the intersection of 3 major tectonic plates, and sitting squarely within the most volcanically and seismically active region of the entire Ring of Fire, contains approximately 130 active volcanoes, more than any other nation on Earth, and has experienced more volcanic eruptions in the historical record than any other country, making its specific geological character both the foundation of the extraordinary agricultural abundance that has supported one of the world's most densely populated regions for thousands of years, and the source of some of the most catastrophic volcanic disasters in human history. The specific tectonic configuration that produces Indonesia's extraordinary volcanic density is the convergence of the Indo-Australian plate, the Eurasian plate, and the Pacific plate in a complex zone of subduction whose multiple trenches and island arcs have generated, over tens of millions of years, the volcanic chain that runs the length of the archipelago and includes some of the most historically significant volcanoes on Earth. Krakatau, whose 1883 eruption produced the loudest sound in recorded history. Tambora, whose 1815 eruption was the largest in the historical record and produced the year without a summer. Merapi, whose repeated eruptions have threatened the densely populated region around Yogyakarta on Java for centuries. Sinabung, whose reawakening after 4 centuries of dormancy beginning in 2010, demonstrated the specific danger of volcanoes that have been quiet long enough for their hazard to be forgotten by the populations that have grown up in their shadow. And the ongoing submarine volcano Anak Krakatau, the child of Krakatau, whose 2018 flank collapse generated the tsunami that struck without warning on the evening of December 22, killing more than 400 people who were attending a beach concert on the Sunda Strait coast. The specific challenge of volcanic risk management in Indonesia, the difficulty of maintaining awareness of volcanic hazard across a population of 270 million people, spread across an archipelago of extraordinary geographic and cultural diversity, many of whom live within the direct hazard zones of active volcanoes because the volcanic soils provide the only reliable agricultural base available to them, is one of the most complex and most consequential problems in applied volcanology anywhere in the world. Fact 52. Volcanic ash, the hazard that travels furthest. Volcanic ash, the term applied to the fine fragments of volcanic rock, glass and mineral crystals, less than 2 millimeters in diameter, that are produced by the fragmentation of magma during explosive volcanic eruptions, and dispersed by eruption columns and atmospheric winds across distances ranging from the immediate vicinity of the erupting vent to the entire circumference of the globe, is the volcanic hazard with the greatest geographic reach. The widest variety of effects on human infrastructure and health, and in some respects the most complex risk management challenges, because its specific behavior in the atmosphere and its specific consequences for the systems it affects depend on a greater number of interacting variables than almost any other volcanic phenomenon. The production of volcanic ash begins with the fragmentation of magma, either by the explosive decompression of dissolved gases as the magma rises and pressure decreases, shattering the melt into tiny glass shards, or by the explosive interaction of magma with external water in phreatomagmatic eruptions that produce particularly fine-grained ash of exceptional hazardousness. The resulting ash particles, carried upward in the eruption column by the turbulent convective motion of hot volcanic gases, are injected into the atmosphere at heights that range from a few kilometers in small eruptions to more than 30 kilometers in the largest explosive events, where the stratospheric winds carry them around the globe in days to weeks. The specific hazards that volcanic ash presents to human systems are numerous and diverse. The abrasive, silica-rich particles damage the turbine blades and fuel systems of jet engines, creating the specific aviation hazard demonstrated most dramatically by the Eyjafjallajökull eruption of 2010. The weight of accumulated ash deposits collapses roofs, particularly when wet, killing people and buildings that show no other sign of structural damage. The fine particles, when inhaled, penetrate deep into the respiratory system and cause silicosis and other respiratory diseases with chronic exposure. And the chemical components leached from ash by rainfall contaminate water supplies and damage agricultural crops across areas far downwind of the erupting volcano. The 1991 Pinatubo eruption deposited ash across an area of approximately 125,000 square kilometers of the Philippines, disrupting agriculture and water supplies for months after the eruption itself had ended. Fact 53. The volcanic history of Mars, a planet that burned bright and went cold. Mars, the fourth planet from the Sun, whose current surface is a cold, largely geologically inactive desert, whose thin atmosphere provides negligible protection against cosmic radiation, and whose surface pressure is less than 1% of Earth's, preserves in its landscape one of the most complete and most accessible records of ancient volcanic activity available anywhere in the solar system, a geological archive of a planet that was, in its early history, far more volcanically active than it is today, and whose specific volcanic history has left structures, deposits, and chemical signatures that tell a story of a world that was briefly and dramatically more hospitable than the one that modern spacecraft explore. The most prominent volcanic structures on Mars are the four great shield volcanoes of the Tharsis Plateau: Olympus Mons, Ischrius Mons, Pavonis Mons, and Arsia Mons, whose specific formation required the accumulation of enormous volumes of basaltic lava over billions of years of repeated eruption from hotspots that, in the absence of plate tectonics, remain stationary beneath the same point of the Martian crust throughout the planet's geological history. The absence of plate tectonics on Mars is the key difference between Martian and terrestrial volcanism in terms of the structures produced. Where the movement of Earth's tectonic plates carries the crust away from hotspots, limiting the growth of individual volcanic structures and distributing volcanic activity across the globe, the stationary Martian crust has allowed the Tharsis volcanoes to grow to their extraordinary dimensions by concentrating billions of years of erupted material in a single location. The evidence for ancient volcanic activity on Mars is not limited to the surface structures visible in orbital imagery. The specific chemical composition of the Martian atmosphere, with its traces of sulfur compounds and the specific isotopic ratios of certain elements, records the outgassing history of a planet that once had a much more active volcanic interior, and the volcanic plains that cover large areas of the Martian surface preserve the record of eruptions that may have, in the planet's early history, produced a thicker atmosphere and liquid water on the surface, conditions that, if they persisted for sufficient time, might have supported the origin of life on a world that is today as cold and as dry as the most hostile desert on Earth. Fact 54. Living with volcanoes, the communities that stay. The specific human experience of living in permanent proximity to an active volcano, of building a home, raising a family, farming the land, and organizing the rhythms of daily life within the direct hazard zone of a geological system capable of destroying everything with little or no warning, is an experience shared by tens of millions of people across the volcanic zones of the world, and one whose specific character, whose particular mixture of practical accommodation, cultural adaptation, and the specific psychological relationship with risk that long familiarity produces, has been documented by anthropologists, geographers, and journalists in a literature that reveals both the extraordinary resilience of human communities in the face of geological hazard and the specific social and economic forces that make relocation away from volcanic hazard zones so persistently difficult to achieve. The communities on the slopes of Mount Merapi in central Java, the most active and most densely populated volcanic hazard zone in Indonesia, where approximately 1 million people live within the direct impact area of the volcanoes' most dangerous eruptive products, represent perhaps the most thoroughly documented example of the specific adaptation strategies that volcanic communities develop over generations of coexistence with an active geological system. The Javanese communities of the Merapi region have developed, over centuries of living with the volcano's periodic eruptions, a specific cultural framework for understanding and managing the volcanic risk that combines practical risk reduction measures, the maintenance of escape routes, the organization of community warning systems, the specific agricultural practices that allow rapid recovery after eruption-related disruptions, with a religious and cosmological tradition that incorporates the volcano into a broader framework of meaning, identifying the specific spiritual dimensions of a mountain that is simultaneously the source of the agricultural fertility on which the community depends and the potential source of the destruction that periodically threatens it. The specific figure of the Juru Kunsai, the keeper of the key, the traditional guardian of the relationship between the community and the volcano, whose role combines practical knowledge of the volcano's behavior with a spiritual responsibility for maintaining the specific relationship between the human and the volcanic that the Javanese cosmological tradition requires, is one of the most remarkable examples of the cultural adaptation of human communities to volcanic coexistence available anywhere in the world. Fact 55. Obsidian, volcanic glass that changed human history. Obsidian, the naturally occurring volcanic glass formed by the rapid cooling of silica-rich rhyolitic or dacitic lava that prevents the crystallization of the melt and produces instead a smooth, isotropic, jet black or occasionally brown, green or banded material of extraordinary hardness, and most importantly for its human uses, extraordinary sharpness when fractured, was one of the most valued raw materials in the prehistoric world. Traded across distances of hundreds to thousands of kilometers from its volcanic source outcrops to the communities that needed its specific cutting properties, and whose specific distribution patterns in the archaeological record have provided prehistorians with one of the most powerful tools available for reconstructing the trade networks and social connections of prehistoric societies that left no written records. The specific property that made obsidian so valuable to prehistoric human communities was the specific character of its fracture, the conchoidal fracture pattern that is produced when a glassy material is struck with a hammerstone, creating curved, extremely sharp edges whose cutting ability exceeds that of any metal blade available before the development of high-carbon steel, and which can be refined by the specific technique of pressure, flacking into tools of extraordinary precision and thinness. The cutting edge of an obsidian blade, examined under scanning electron microscope, is smoother and sharper than any steel surgical scalpel, a fact that has led to the experimental use of obsidian blades in modern surgery, where their specific cutting properties produce incisions with less tissue trauma than conventional steel instruments. The archaeological distribution of obsidian in the prehistoric Mediterranean, Near East, and Mesoamerica records the specific geography of volcanic sources, the obsidian outcrops of Lipari in the Aeolian Islands, Milos in the Aegean, Cappadocia in Anatolia, and Obsidian Cliff in Yellowstone. and the specific reach of the trade networks that carried this volcanic material from its geological origins to the communities that fashioned it into the tools on which their subsistence and survival depended. Fact 56. Submarine calderas and hidden giants. The ocean floor conceals, beneath its sediment cover and its spreading ridges and its abyssal plains, a population of large volcanic structures whose specific dimensions and geological significance rival those of the most impressive subaerial volcanoes, but whose existence remained largely unknown until the development of ocean floor mapping technologies in the 20th century allowed the systematic survey of a terrain that covers more than 70% of the Earth's surface, and that had been for all of human history before the mid-20th century, as inaccessible to direct observation as the surface of another planet. Among the most significant of the submarine volcanic structures revealed by modern ocean floor mapping are the large oceanic plateaus, the submarine equivalents of the continental flood basalt provinces, formed by the eruption of enormous volumes of basaltic lava on the ocean floor in episodes of exceptional volcanic productivity, whose specific formation has been linked by geologists to the arrival of new mantle plumes at the base of the oceanic lithosphere, and whose potential climate consequences, through the release of volcanic gases into the ocean and ultimately the atmosphere, have been proposed as contributing factors to several of the major climate and extinction events of the geological record. The Ontong Java Plateau in the Western Pacific, the largest oceanic plateau on Earth, covering an area of approximately 1.9 million square kilometers and rising approximately 2 kilometers above the surrounding ocean floor, was formed approximately 120 million years ago in what was probably the most voluminous volcanic event of the past 250 million years, erupting an estimated 44 million cubic kilometers of basaltic lava over a period of a few million years. The specific climatic consequences of the Ontong Java event, the carbon dioxide and sulfur dioxide released by an eruption of this scale, have been proposed by geologists as a contributing factor to the oceanic anoxic event of the early Cretaceous period, a major disruption of ocean chemistry that caused significant changes in the marine fossil record of the period. Fact 57. Volcanoes and mythology, the stories cultures told. Across every culture that has lived within sight of volcanic activity, the specific phenomena of erupting mountains, the fire, the ash, the ground shaking, the destruction, and the subsequent renewal, have generated mythological traditions of extraordinary richness and diversity, each one expressing in cultural terms the specific relationship between a particular human community and the particular volcanic landscape it inhabited, and each one demonstrating the universal human impulse to find meaning and narrative in the most overwhelming expressions of natural power. In ancient Greece, the volcanic phenomena of the Mediterranean, the Phlegraean fields, Etna, the erupting vents of the Aeolian Islands, were woven into the mythological fabric with a thoroughness that made volcanic fire a fundamental element of the Greek cosmological imagination. The forge of Hephaestus, the creation of humans from clay shaped at divine fire, the titans imprisoned beneath the volcanic mountains of the earth, all expressed in mythological terms the specific Greek perception of volcanic fire as a divine and creative force whose specific character was simultaneously destructive and generative, dangerous and necessary. In the mythological traditions of the Pacific, where the volcanic landscapes of Hawaii, New Zealand, Vanuatu, and the other islands of the volcanic Pacific are among the most dramatically active on Earth, volcanic deities, whose specific characters reflect the specific behavior of the volcanoes they represent, have been central to the cosmological traditions of the communities that have lived alongside them. The Hawaiian Pele, goddess of volcanoes, creator and destroyer, her home the Kilauea caldera, her body the lava that flows to the sea, is one of the most complex and most fully developed volcano deities in any tradition. A figure whose specific mythological character captures with remarkable precision the specific paradox of volcanic activity, the fact that the same force that destroys existing land and kills existing life also creates new land, and over geological time, the new soils on which new life eventually grows. Fact 58. Calderas, when volcanoes collapse into themselves. The caldera, the large volcanic depression, formed not by the eruption of material to build a cone, but by the catastrophic collapse of a volcanic edifice into the emptied space, left by the rapid eruption of a large volume of magma from the chamber below, is among the most dramatic and most geologically significant of all volcanic structures, producing landscapes of extraordinary scale and beauty that bear no resemblance to the classic conical volcano of popular imagination, and whose specific dimensions, typically measured in kilometers to tens of kilometers rather than the meters of a conventional volcanic crater, reflect the enormous volumes of magma whose rapid evacuation during caldera-forming eruptions produces the collapse that gives these structures their form. The specific mechanism of caldera formation begins with the rapid eruption, in hours to days during the most violent examples, of a sufficient volume of magma from the chamber below the volcano to leave the overlying rock without adequate support, at which point the roof of the chamber collapses inward along ring fractures that define the caldera's margins, dropping the overlying terrain by tens to hundreds of meters in a geological instant. The resulting structure, a broad, flat-floored depression bounded by steep caldera walls and frequently occupied by a crater lake, or in the case of calderas formed over still-active magmatic systems, by continued volcanic activity within the caldera floor, has a specific aesthetic character entirely different from the volcano that preceded it. Vast, open, and ancient feeling in a way that the classic volcanic cone, with its suggestion of upward aspiration, is not. The Ngorongoro caldera in Tanzania, approximately 19 kilometers in diameter, formed approximately 2 to 3 million years ago, and now occupied by one of the most remarkable wildlife sanctuaries on Earth, is perhaps the most biologically extraordinary caldera on the planet, its enclosed environment supporting the highest density of large mammalian predators anywhere in Africa and preserving, within the specific geography of its caldera walls and floor, an ecosystem of exceptional completeness and stability whose specific character is a direct consequence of the volcanic event that created it. Fact 59. Volcanic rocks, reading the Earth's autobiography. The rocks produced by volcanic activity, the igneous rocks whose specific mineralogy, texture, and chemistry record the specific conditions of temperature, pressure, and composition that existed in the magma from which they solidified, are the primary documents through which geologists read the history of the Earth's interior, interpreting in the specific character of each rock, sample the conditions that existed in the magma chamber, the conduit system, and the eruption environment that produced it, and reconstructing from the distribution of volcanic rocks across the landscape the sequence of geological events that shaped the terrain over millions and billions of years. The most abundant volcanic rock on Earth is basalt, the dark, fine-grained rock produced by the rapid cooling of low silica, high-temperature magma at the surface, forming the ocean floors, the Hawaiian shield volcanoes, the flood basalt provinces, and the lava flows of continental rift zones worldwide, and constituting the fundamental building material of the oceanic crust that covers approximately 70% of the Earth's surface. The specific mineralogy of basalt, dominated by the calcium-rich feldspar plagioclase and the iron and magnesium-rich minerals pyroxene and olivine, reflects the specific chemical composition of the upper mantle from which basaltic magmas are derived, making basalt the most direct chemical message that the mantle sends to the surface. Rhyolite, the silica-rich volcanic rock produced by the cooling of the most evolved and most viscous magmas, typically associated with the most explosive volcanic eruptions, is the volcanic equivalent of granite, formed when a magma that has undergone extensive crystal fractionation and crustal assimilation reaches the surface rather than solidifying at depth. The specific textures of volcanic rocks, the vesicles formed by gas bubbles trapped during solidification, the phenocrysts of large crystals embedded in a fine-grained groundmass, the flow banding produced by the movement of viscous lava, are a direct record of the physical processes that accompanied the magma's ascent and eruption, preserving in stone the specific history of a geological event that may have occurred millions of years ago. Fact 60. The volcanoes at 60, 40 facts from the summit. 60 facts into the story of the volcanoes, and the arc of what remains has come clearly into view. We have covered the fundamental geology, the great historical eruptions, the volcanic landscapes of the world's most active regions, the specific ways in which volcanic activity intersects with human civilization, through the soil, through the hazard, through the cultural and mythological traditions that every volcanic culture has developed to make sense of the mountains of fire in their midst. We have understood that obsidian from a volcanic outcrop in the Aeolian Islands traveled to the communities of prehistoric Europe as a trade good, whose specific cutting properties no other material could match. We have stood inside the Ngorongoro caldera and understood that the most biodiverse wildlife sanctuary in Africa is the direct consequence of a volcanic collapse that occurred 2 to 3 million years ago. We have listened to the earth breathe through the fumaroles of the Campi Flegrei and understood that beneath the western suburbs of Naples lies a volcanic system whose next major eruption, whenever it comes, will be among the most consequential geological events in the history of European civilization. 40 facts remain. They will carry us to the summits and the depths that the first 60 have prepared us to understand, the most remote and most extraordinary volcanic landscapes on Earth, the stories of survival and loss that volcanic eruptions have generated throughout human history, and the specific beauty of a planet that has been on fire for 4.5 billion years and shows no sign of going out. This is explored during sleeping. Fact 61, Mount Pinatubo's aftermath, how the land recovers. The landscape around Mount Pinatubo in the years and decades following the catastrophic eruption of June 1991, the scarred, ash-grey terrain of pyroclastic deposits, the lava-filled river valleys choked with volcanic sediment, the former agricultural land buried under meters of volcanic material, and the communities whose displacement from the immediate volcanic zone initiated a process of social and economic disruption, whose consequences extended far beyond the eruption itself, tells a story not only of volcanic destruction, but of the extraordinary capacity of both natural ecosystems and human communities to recover from catastrophic geological events, a recovery that is neither simple nor rapid nor without its specific costs. But that demonstrates with consistent force the resilience that living systems, biological and social, bring to the challenge of rebuilding after catastrophe. The ecological recovery of the Pinatubo landscape has been documented in detail by biologists who have tracked the return of vegetation and wildlife to the devastated area since 1991, finding a pattern of primary succession, the colonization of bare volcanic substrate by pioneer plant species, followed by the gradual development of more complex plant communities that broadly mirrors the ecological recovery documented on Surtsey and other volcanic landscapes. But compressed into a tropical timeline whose higher rainfall, higher temperatures, and proximity to intact forest patches have accelerated the recolonization process significantly compared to the Icelandic example. Within 5 years of the eruption, significant vegetation had returned to the margins of the pyroclastic flow deposits. Within a decade, secondary forest was establishing itself on the older and more weathered portions of the deposits, and by the second decade, large areas of the former devastation zone were supporting forest communities of increasing structural complexity. The human recovery has been more complicated. The Ita indigenous people, who had lived on the slopes of Pinatubo for generations, and whose intimate knowledge of the mountain's behavior had been largely dismissed by the emergency management authorities before the eruption, were displaced to lowland resettlement sites, whose specific agricultural and cultural conditions were profoundly unsuited to a community whose entire way of life had been adapted to the volcanic highland environment, and whose experience of post-eruption displacement represents one of the most thoroughly documented examples of the specific social costs that volcanic disasters impose on the most vulnerable populations in their path. Fact 62, the Mid-Atlantic Ridge, the longest mountain range on Earth. The Mid-Atlantic Ridge, the continuous underwater mountain chain that runs approximately 16,000 kilometers from the Arctic Ocean in the north to the southern tip of Africa in the south, passing through the center of the Atlantic Ocean basin along a line that broadly mirrors the coastlines of the continents on either side of it, and whose specific geological character as the boundary between the North American and Eurasian plates in the north and the South American and African plates in the south makes it one of the most volcanically productive linear features on the surface of the Earth, is both the largest mountain range on the planet and the geological structure most directly responsible for the specific shape of the Atlantic Ocean, whose width has been increasing at a rate of approximately 2 to 3 centimeters per year for the past 180 million years, as new ocean floor is continuously created at the ridge crest and the continents on either side are pushed apart. The volcanism of the Mid-Atlantic Ridge is fundamentally different in character from the explosive eruptions of the Ring of Fire's subduction zones. The spreading center environment, where two plates are pulling apart rather than colliding, produces effusive eruptions of fluid basaltic lava that emerge from fissures and central vents along the ridge crest and spread laterally to form the new oceanic crust that constitutes the floor of the Atlantic Ocean. The specific process of seafloor spreading, the continuous creation of new ocean floor at the ridge and its gradual movement away from the ridge axis as yet more new floor is created behind it, was one of the key lines of evidence that led to the development of the theory of plate tectonics in the 1960s, as the specific pattern of magnetic reversals recorded in the ocean floor on either side of the ridge mirror images of each other. Reflecting the alternating polarity of the Earth's magnetic field, at the time each strip of ocean floor solidified from its erupted magma, provided a direct and quantitative record of the rate and history of seafloor spreading that made the theory of plate motion essentially inescapable. Iceland, where the Mid-Atlantic Ridge crosses above sea level, offers the only place on Earth where it is possible to stand on the exposed surface of a mid-ocean spreading center, to walk across the Rift Valley, where the Eurasian and North American plates are separating, and to experience directly the specific geological process that has been reshaping the surface of the Earth for hundreds of millions of years. Fact 63. Volcanic hazard maps, drawing the boundaries of danger. The volcanic hazard map, the scientific and cartographic product that represents the geographic distribution of specific volcanic hazards around an active or potentially active volcano, translating the geological understanding of a volcanic system's behavior and the numerical models of potential eruption scenarios into a spatial representation accessible to civil protection authorities, land use planners, and the public, is one of the most consequential practical outputs of modern volcanological science, and one whose specific quality and accuracy have direct implications for the human cost of volcanic disasters in the communities that rely on them for risk management decisions. The production of a volcanic hazard map requires the integration of multiple streams of geological and geophysical information. The eruptive history of the volcano, as reconstructed from the geological record of past deposits, whose specific distribution, thickness, and character constrain the likely size, style, and frequency of future eruptions. The topography of the surrounding landscape, which determines the specific paths that lava flows, pyroclastic flows, and lahars will follow when they leave the volcanic edifice, the prevailing wind patterns that control the distribution of volcanic ash, and the output of numerical models that simulate the behavior of specific volcanic phenomena under the conditions expected for the eruption scenarios considered most likely or most consequential. The specific challenge of volcanic hazard mapping lies in the fundamental uncertainty that attaches to all forecasts of future volcanic behavior. Volcanoes are complex, nonlinear systems whose specific future behavior cannot be predicted with the same confidence that weather forecasting or hydrological modeling achieves, and in the specific difficulty of communicating that uncertainty to the non-specialist audiences who must act on it. The hazard maps produced for the areas surrounding Vesuvius, the Campi Flegrei, Mount Rainier in Washington state, and other high-consequence volcanic systems represent some of the most carefully constructed and most consequentially uncertain documents in the entire field of applied Earth science. Maps that will, when the next major eruption occurs, be judged against the reality of the event with a specificity and a consequence that no other scientific document routinely faces. Fact 64. The volcanic Canary Islands, islands born of the deep. The Canary Islands, the archipelago of 7 major islands and several smaller islets located in the North Atlantic Ocean, approximately 100 kilometers west of the southern coast of Morocco, forming part of the territory of the Kingdom of Spain and serving as one of the most visited tourist destinations in Europe, are among the most geologically young and most volcanically active island groups in the Atlantic Basin. Their specific geological character, as the surface expression of a long-lived mantle hotspot, making them a dynamic and continuously evolving volcanic archipelago whose specific eruptions, while less frequent than those of the Hawaiian or Indonesian volcanic systems, have demonstrated in the modern era a capacity for significant impact on both the local population and the wider regional environment. The most recent significant eruption in the Canary Islands, the eruption of the Cumbre Vieja volcanic system on the island of La Palma that began on September 19, 2021, and continued for 85 days before ending on December 13, 2021, making it the longest eruption in La Palma's recorded history, produced lava flows that destroyed approximately 3,000 buildings, covered approximately 12 square kilometers of the island's western coast with new volcanic material, displaced approximately 7,000 residents from their homes, and extended the island's southwestern coastline approximately 50 hectares into the sea, with the new land created by lava reaching the ocean. The specific character of the 2021 La Palma eruption, its duration, the volume of lava it produced, the specific paths taken by the lava flows through densely settled agricultural land, was broadly consistent with the behavior predicted by the volcanic hazard assessments prepared before the eruption, validating in a specific and consequential way the specific science that underlies volcanic hazard assessment while simultaneously demonstrating, with the intimate human scale of individual homes buried under meters of basaltic lava, the specific cost that even a well-anticipated and well-managed volcanic eruption imposes on the communities in its path. Fact 65. Antarctica's volcanoes fire beneath the ice. Antarctica, the frozen continent at the bottom of the world, whose ice sheet covering approximately 98% of its land surface in a layer averaging approximately 2,160 meters in thickness, represents the largest single body of ice on Earth and the most extreme terrestrial environment available to geological investigation. Conceals beneath its ice a volcanic history whose specific extent and character have been substantially revealed only in recent decades by the application of airborne geophysical survey techniques capable of imaging the bedrock beneath the ice sheet, and whose specific implications for the stability of the ice sheet under conditions of future volcanic activity have become an increasingly active area of glaciological research, as the specific consequences of ice sheet instability for global sea level have become more clearly understood. The most accessible and most thoroughly studied of Antarctica's active volcanoes is Mount Erebus on Ross Island, the southernmost active volcano on Earth, whose summit elevation of 3,794 meters above sea level places it above the level of permanent ice, and whose persistent summit lava lake, one of only 5 known on Earth, has been the subject of continuous scientific monitoring since the establishment of permanent research camps on the island in the 20th century. The lava lake of Erebus, approximately 40 meters in diameter, its surface in constant slow convective motion, occasional strombolian bursts ejecting lava bombs onto the crater rim, exists in one of the most extreme environments on Earth, the Antarctic atmosphere, adding to the already considerable challenges of conducting research at an active volcanic summit a wind chill factor that can reduce effective temperatures to below -60 degrees Celsius. Beneath the main Antarctic ice sheet, the application of airborne ice-penetrating radar and magnetic surveys has revealed a subglacial volcanic province of unexpected extent in West Antarctica, a region of the ice sheet underlain by approximately 138 volcanoes identified in a 2017 survey, making it one of the densest concentrations of volcanoes on Earth. Most of them buried beneath kilometers of ice, and therefore invisible from the surface, but potentially capable, if any were to erupt beneath the ice, of locally accelerating the melting of the overlying ice sheet in ways that could contribute to sea level rise. Fact 66. The volcanic origin of the atmosphere, breathing volcanic air. The atmosphere of the Earth, the specific mixture of nitrogen, oxygen, argon, carbon dioxide, water vapor, and trace gases that surrounds the planet, makes it habitable for life, moderates its surface temperature through the greenhouse effect, and protects its surface from the most damaging wavelengths of solar radiation, is, in its fundamental chemical composition and in the specific history of its development over the 4.5 billion years of the Earth's existence, a volcanic product. The accumulated output of billions of years of volcanic degassing that has released from the Earth's interior the specific volatile compounds, water, carbon dioxide, nitrogen, sulfur dioxide, and others, that, through the subsequent processes of atmospheric chemistry, biological activity, and geological cycling, have been transformed into the atmosphere that every living organism on the planet breathes today. The specific process by which volcanism built the Earth's early atmosphere is called outgassing, the release of dissolved gases from magma as it rises toward the surface and the confining pressure decreases, and their subsequent escape from the Earth's interior into the atmosphere through volcanic vents, fumaroles, and mid-ocean ridge systems. In the earliest period of the Earth's history, the planet's surface was so extensively covered by volcanic activity, the heat generated by planetary accretion, core formation, and the late heavy bombardment maintaining a surface environment of near-global magmatic activity, that outgassing was effectively continuous and on a scale that dwarfs anything in the subsequent geological record. The early atmosphere produced by this primordial outgassing was fundamentally different from the modern one, rich in water vapor, carbon dioxide, nitrogen, and sulfur compounds, but almost entirely lacking in the free oxygen that constitutes approximately 21% of the modern atmosphere and on which the metabolism of all aerobic organisms depends. The accumulation of oxygen in the atmosphere beginning approximately 2.4 billion years ago, the Great Oxidation Event, was not a volcanic product, but a biological one, the consequence of the evolution of photosynthesis by cyanobacteria, whose specific metabolic process released oxygen as a byproduct, and whose population explosion over hundreds of millions of years eventually transformed the atmospheric chemistry of the entire planet, poisoning the anaerobic organisms that had previously dominated the biosphere and creating the specific atmospheric environment in which complex multicellular life would eventually evolve. Fact 67. Volcanic national parks, protected landscapes of fire. The specific recognition by governments across the volcanic world that the landscapes created by volcanic activity possess aesthetic, scientific, and ecological values of sufficient significance to warrant formal protection from development and exploitation. The establishment of volcanic national parks, nature reserves, and UNESCO World Heritage sites around the world's most significant volcanic features represents one of the most consequential intersections of volcanological science. conservation biology, and public policy in the modern era, creating protected areas whose specific character as simultaneously geological monuments, ecological laboratories, and public education resources makes them among the most valuable and most visited natural areas on Earth. Hawaii Volcanoes National Park, established in 1916 as one of the first national parks in the United States, specifically to protect a volcanic landscape, encompassing the summits and flanks of both Kilauea and Mauna Loa, and covering approximately 1,350 square kilometers of the Big Island's volcanic terrain, is the most visited and most scientifically productive volcanic national park in the world. Receiving approximately 2 million visitors annually, and serving as the field laboratory for the United States Geological Survey's Hawaiian Volcano Observatory, whose century of continuous monitoring has produced the world's most detailed long-term record of volcanic behavior. The park's specific character, the accessibility of active lava flows to visitors at certain stages of eruption, the dramatic landscape of recent and ancient lava fields, the surviving native Hawaiian ecosystems on the older volcanic soils, and the cultural significance of the landscape in Hawaiian tradition, makes it one of the most complete expressions of the full range of volcanic values, geological, ecological, and cultural, available in any protected area on Earth. Tongariro National Park in New Zealand, the first national park established in New Zealand, gifted to the nation in 1887 by the Maori chief Te Huhu Tukino IV, who described the volcanic peaks of the Tongariro Massif as the backbone of his people, was designated a UNESCO World Heritage Site in 1993, the first property to receive dual inscription for both its natural and its cultural values. Recognizing simultaneously the extraordinary volcanic landscape and the specific Maori cultural and spiritual significance of the mountains that New Zealand's volcanic heritage has created. Fact 68. The volcanic Mediterranean, how fire shaped Western civilization. The volcanic geology of the Mediterranean basin, the specific distribution of volcanic systems across the region, from the Azores and Canary Islands in the west through the volcanic fields of Spain, France, and the Massif Central, the Italian volcanic province including Vesuvius, the Campi Flegrei, Etna, and Stromboli, the volcanic arc of the Aegean including Santorini and Nisyros, and the volcanic fields of Turkey and the Levant in the east, has been an active and consequential presence throughout the entire span of Mediterranean civilization, shaping the physical landscape in which the cultures of ancient Egypt, Greece, Rome, and their successors developed, providing in the fertile volcanic soils of southern Italy, Sicily, and the Aegean Islands the agricultural foundation on which some of the most influential civilizations in human history built their prosperity. And punctuating the historical record with eruptions whose specific consequences, the destruction of Pompeii, the possible disruption of Bronze Age Aegean civilization by the Santorini eruption, the famines and plagues associated with volcanic winters, have shaped the political and cultural history of the region in ways that historians are still working to fully understand. The specific fertility of the volcanic soils of Campania, the region of southern Italy surrounding Naples whose volcanic geology, produced by the activity of Vesuvius and the Campi Flegrei, has supported agricultural productivity of exceptional quality throughout the historical period, was recognized explicitly by Roman agricultural writers who attributed the renowned quality of Campanian wine, olive oil, and wheat to the specific mineral richness of the volcanic soils, and who understood, at least implicitly, that the agricultural abundance of the region was inseparable from the volcanic hazard that periodically threatened it. The destruction of Pompeii was not the destruction of an impoverished or marginal community, but of one of the most prosperous and most commercially active cities in the Roman Empire, a prosperity built directly on the volcanic soils whose fertility had attracted settlers to the shadow of Vesuvius in the first place, and whose loss in 79 CE was, among its many other dimensions, the specific destruction of an agricultural system whose recovery took generations. Fact 69. Volcanoes and diamonds, the deepest deliveries. Among the more unexpected products of volcanic activity is the specific geological process by which diamonds, the carbon crystals formed at depths of approximately 150 to 200 kilometers beneath the Earth's surface, under conditions of pressure and temperature available only in the lithospheric mantle, and the hardest naturally occurring material on Earth, are delivered from their formation depth to the surface in a specific type of volcanic eruption, whose extraordinary speed and specific character make it unlike any other volcanic process, and whose geological products, the kimberlite pipes and lamproite pipes that are the primary sources of mined diamonds worldwide, are the deepest material samples of the Earth's interior available for direct study at the surface. The volcanic process that delivers diamonds to the surface is the kimberlite eruption, a rare and geologically unusual type of volcanic event in which magma originating at very great depth in the mantle ascends through the lithosphere at extraordinarily high velocity, driven by a high content of carbon dioxide and water that expands explosively as the magma rises and pressure decreases, carrying with it fragments of the deep mantle rock through which it passes, including, occasionally, the diamonds that have crystallized in that rock over billions of years. The velocity of kimberlite magma ascent, estimated at between 10 and 30 meters per second, compared to the much slower ascent rates of conventional volcanic magmas, is what preserves the diamonds intact rather than allowing them to revert to graphite, the stable form of carbon at surface pressures, during the ascent. The specific geological evidence for kimberlite eruptions, the carrot-shaped pipes of kimberlite rock that represent the solidified remnants of the eruption conduits, is found exclusively in the ancient, stable cores of continents called cratons, whose specific geological character provides the specific deep lithospheric roots in which diamond formation occurs, and from which kimberlite eruptions have periodically delivered the Earth's most precious geological cargo to the surface throughout the past 3 billion years. Fact 70, the volcanoes at 70, 30 facts from the end. 70 facts into the story of the volcanoes, and the depth and the breadth of what this subject contains has become fully apparent. We have traveled from the primordial outgassing that built the Earth's first atmosphere to the specific kimberlite eruptions that deliver diamonds from the mantle to the surface. We have stood at the rim of Erebus in Antarctic darkness and watched a lava lake that has been burning continuously since before any living person was born. We have understood that the volcanic soils of Campania built Roman prosperity, and that the same volcanic system that sustained it destroyed Pompeii, and that the people who rebuilt on those soils in the generations after 79 CE made the same rational calculation that every volcanic community has made throughout human history. That the fertility is worth the risk, that the abundance of the present is worth the uncertainty of the future, that the volcano is not an enemy but a landlord whose terms are severe and whose tenure is very long. 30 facts remain. They will carry us through the final and deepest dimensions of the volcanic story, the science of prediction, the communities that have survived the worst, the specific landscapes of volcanic beauty that no other geological process can create, and the question that every person who has spent time with this subject eventually comes to. What does it mean that we live on the surface of a planet that is still, after 4.5 billion years, generating the heat and the motion that drives the fires beneath our feet? The answer is not reassuring, but it is magnificent. This is explored during sleeping. Fact 71, Nyiragongo, the world's most dangerous lava lake. Mount Nyiragongo, the active stratovolcano in the Democratic Republic of Congo, rising to 3,470 meters above sea level in the Virunga Mountains on the western branch of the East African Rift, whose summit crater contains the world's largest and most persistently active lava lake. A body of molten basaltic lava approximately 200 meters in diameter, whose surface level rises and falls with the activity of the underlying magmatic system, and whose specific geological character, the extraordinarily low silica content and high alkali content of the nephelinite lava that feeds it, producing a melt of exceptional fluidity, unlike any other lava type commonly encountered on Earth, makes it the source of the most rapidly moving lava flows in the historical record, and one of the most acutely dangerous volcanic systems on the planet for the large populations living in its immediate vicinity, has produced 2 catastrophic drainage events in the modern era whose specific character demonstrated with devastating clarity. The unique hazard that a high-standing lava lake in a populated volcanic region represents. The first catastrophic drainage of the Nyiragongo lava lake occurred on January 10, 1977, when fractures opened in the crater walls and allowed the lava lake to drain in less than 1 hour, releasing a flood of extremely fluid lava down the volcano's flanks at estimated speeds of up to 60 kilometers per hour, faster than a person can run, faster than most vehicles can navigate the unpaved roads of the region, killing an estimated 600 to 2,000 people in the communities on the volcano's lower slopes before the flow reached the valley floors and slowed. The second drainage event occurred on January 17, 2002, when a 10-kilometer-long fissure opened on the volcano's southern flank, producing lava flows that advanced through the city of Goma, a city of approximately 400,000 people on the shore of Lake Kivu, destroying approximately 15% of the city's buildings, forcing the evacuation of approximately 400,000 people, and ultimately flowing into Lake Kivu and raising concerns about the possible destabilization of the lake's deep layers of dissolved carbon dioxide and methane, whose release in a limnic eruption would represent a catastrophic hazard to the approximately 2 million people living on the lake's shores. Nyiragongo erupted again in May 2021, sending lava flows toward Goma for the second time in 20 years, and reinforcing the specific urgency of the ongoing debate about whether a city of Goma's size should exist in its current location. Fact 72. The Volcanic History of North America, a continent on fire. The volcanic history of North America, the record of volcanic activity across a continent whose geological diversity encompasses the subduction-driven explosive volcanism of the Cascade Range, the hotspot volcanism of Yellowstone and the Snake River Plain, the extensional volcanism of the Basin and Range Province, the monogenetic volcanic fields of the southwestern United States and Mexico, and the flood basalt provinces of the Columbia Plateau and the Deccan-equivalent Siberian-scale eruptions of the geological past, is one of the richest and most varied in the world, and one whose specific recent chapter, the period since the last ice age, includes eruptions of sufficient size and frequency to have profoundly influenced the landscape, the ecology, and in some cases the human history of the continent. The Cascade Range, the chain of stratovolcanoes running from northern California through Oregon and Washington to southern British Columbia, including Mount Shasta, Mount Hood, Mount Rainier, Mount St. Helens, and Mount Baker in the United States and Mount Garibaldi and others in Canada, is the product of the subduction of the Juan de Fuca Plate beneath the North American Plate along the Cascadia subduction zone, and represents in the assessment of the United States Geological Survey the volcanic system posing the greatest potential hazard to the largest population of any volcanic region in the United States. Mount Rainier, the highest peak in the Cascade Range at 4,392 meters, a massive stratovolcano whose specific hazard derives not only from its potential for explosive eruptions, but from the enormous volume of glacier ice and hydrothermally altered rock on its flanks that could, in a major eruption or even a significant flank collapse without an eruption, generate lahars of sufficient volume to inundate the densely populated valleys downstream, has been identified by volcanologists as one of the 16-decade volcanoes designated by the International Association of Volcanology and Chemistry of the Earth's interior as meriting priority study because of their combination of destructive history and proximity to large populations. The Columbia River basalts, the flood basalt province covering approximately 210,000 square kilometers of Washington, Oregon, and Idaho, erupted between approximately 17 and 6 million years ago, represent the most recent large igneous province on the North American continent, and a reminder that the scale of volcanic activity that characterized the Earth's geological past has not been entirely left behind. Fact 73. Volcanic prediction, the hardest problem in geoscience. The prediction of volcanic eruptions, the specific scientific challenge of determining, from the monitoring data available at any given moment, whether and when and how a volcanic system will erupt, with sufficient accuracy and sufficient lead time to allow the evacuation of threatened populations and the implementation of emergency response measures, is widely regarded by Earth scientists as one of the hardest problems in the geosciences, and one whose specific difficulty reflects not only the complexity of the physical systems involved, but the fundamental character of the scientific knowledge available and the specific nature of the decisions that volcanic predictions must inform. The specific difficulty of volcanic eruption prediction derives from multiple sources that interact in ways that resist simple resolution. Volcanic systems are genuinely complex, nonlinear physical systems whose behavior is controlled by a large number of interacting variables: magma composition, volatile content, temperature, the geometry of the conduit system, the stress state of the surrounding crust, the history of previous eruptions, and many others, whose individual values are not directly observable and whose interactions are not fully understood. The monitoring data available from even the most thoroughly instrumented volcanic systems provides an indirect and incomplete picture of the state of the system at depth, filtered through the specific sensitivities and limitations of the instruments deployed and the specific models used to interpret their output. And the decisions that volcanic predictions must inform, above all the decision to order or recommend the evacuation of thousands or tens of thousands of people from their homes and livelihoods, involve not only scientific uncertainty, but the specific social, political, and economic costs of evacuation that must be weighed against the specific risks of the eruption being predicted. The specific tragedy of the 1985 Nevado del Ruiz disaster in Colombia, in which a moderate eruption generated lahars that killed approximately 23,000 people in the town of Armeiro, despite the existence of hazard maps that correctly identified the town as being in the lahar hazard zone, was not primarily a failure of volcanic science, but a failure of the specific institutional and communication processes by which scientific knowledge is translated into protective action, a distinction whose importance for the future of volcanic risk management is impossible to overstate. Fact 74. The East African Rift, a continent tearing apart. The East African Rift System, the vast geological structure extending approximately 3,000 kilometers from the Afar Triangle in the north, where the African, Arabian, and Somali plates meet in a triple junction of extraordinary geological complexity, southward through Ethiopia, Kenya, Tanzania, Malawi, and Mozambique to the Zambezi River, and representing the most active continental rift on Earth. A zone where the African continent is being pulled apart by the same tectonic forces that created the Atlantic Ocean and that will, over the next tens of millions of years, separate East Africa from the rest of the continent and create a new ocean basin between them, is one of the most geologically dynamic and most volcanically significant regions on Earth, and one whose specific character as a zone of active continental extension has produced a volcanic landscape of extraordinary diversity, encompassing the lava lakes of Nyiragongo and Eruption, the vast shield volcanoes of the Ethiopian highlands, the calderas of the Kenyan Rift, and the stratovolcanoes of the Virunga chain, as well as the specific geological environments whose specific chemistry has made them candidates for the site of the origin of life. The Afar Triangle, the depression at the northern end of the East African Rift, where three tectonic plates are pulling apart simultaneously, creating a landscape of extraordinary geological activity whose surface already lies below sea level in its lowest portions, and whose specific geological character makes it one of the most direct surface expressions of the processes of continental rifting and early ocean floor formation available anywhere on Earth, contains the Eruption volcano, whose persistently active summit lava lake has been described by the few volcanologists and travelers who have reached it across one of the most inhospitable landscapes on Earth as one of the most overwhelming geological experiences available to a human observer. The specific broader significance of the East African Rift for human history lies in its relationship to human evolution. The Rift Valley environments of East Africa, with their specific combination of grassland, woodland, and lake ecosystems created by the tectonic and volcanic activity of the rift system, provided the specific ecological setting in which the genus Homo evolved, and in which the specific combination of environmental pressures and opportunities drove the development of the cognitive and social capacities that distinguish modern humans from all other primates. Fact 75. Volcanic islands as biodiversity hotspots. The volcanic islands of the world's oceans, the islands that have emerged from the sea as the surface expressions of mantle hotspots or mid-ocean ridge volcanism, geologically young, physically isolated from continental landmasses by vast expanses of open ocean, and colonized by whatever organisms were capable of crossing those ocean barriers by wind, water, or their own locomotion, are among the most important and most intensively studied examples of evolutionary processes in the natural world, providing the specific combination of geographic isolation, ecological opportunity, and geological youth that has driven, on island after island and archipelago after archipelago, the rapid evolution of new species from the small founding populations that were the first colonists of each new volcanic landmass. The Galapagos Islands, the volcanic archipelago approximately 1,000 kilometers west of Ecuador, whose specific combination of geological youth, active volcanism, and biological diversity provided Charles Darwin with some of the most important observations that informed the development of the theory of natural selection during his visit in 1835, are among the most thoroughly studied examples of island evolutionary biology on Earth. Their specific fauna including the 13 species of Darwin's finches, whose adaptive radiation from a single ancestral colonizing population into a diverse array of species occupying different ecological niches, provided one of the clearest demonstrations available in the natural world of the specific mechanism of evolution by natural selection. The Hawaiian Islands, volcanic in origin, isolated in the Central Pacific by the greatest ocean distances on Earth, and colonized by an extraordinarily small number of founding species that subsequently diversified into the most species-rich endemic biota of any island system on Earth, represent the most extreme example of evolutionary radiation driven by volcanic island isolation. With the approximately 10,000 native species of Hawaiian organisms descended from an estimated 400 or fewer founding colonist lineages that successfully crossed the Pacific to reach the islands in the geological past, each one subsequently diversifying in the specific ecological space that the volcanic landscape and the absence of continental competitors provided. Fact 76. The sounds of volcanoes, infrasound, and the inaudible earth. The acoustic phenomena produced by volcanic activity, the specific sounds generated by the movement of magma through conduits, the explosive fragmentation of lava at erupting vents, the collapse of lava tube roofs, the interaction of lava with water, and the resonance of volcanic conduits as gas and fluid move through them, span a frequency range extending from the deepest infrasound, far below the threshold of human hearing, to the explosive detonations of major eruptions audible across thousands of kilometers, and constitute one of the most scientifically productive and most practically useful streams of monitoring data available to volcanologists attempting to understand and predict volcanic behavior. The infrasound produced by volcanic activity, the acoustic waves of frequency below approximately 20 Hz that are generated by the same volcanic processes that produce audible sound, but that propagate through both the atmosphere and the ground at frequencies too low for the human ear to detect, has emerged in the past 2 decades as one of the most valuable tools in the volcanic monitoring toolkit, providing information about the style, intensity, and location of volcanic activity at distances of hundreds to thousands of kilometers from the erupting volcano and at spatial resolutions impossible to achieve with traditional monitoring networks. The specific mechanism by which volcanic infrasound is generated varies with the eruptive process. The explosive bursting of gas bubbles at the surface of a lava lake or in a strombolian eruption produces infrasound pulses whose specific frequency and waveform character encode information about the size and geometry of the exploding bubble. The sustained tremor of a large explosive eruption column produces infrasound of lower frequency and longer duration. And the resonance of volcanic conduits, the specific acoustic behavior of a tube of gas-charged magma vibrating in response to the forces acting on it, produces infrasound signals of characteristic frequency that have been used to estimate the physical dimensions of the conduit system and the properties of the magma it contains. The global network of infrasound monitoring stations, established under the Comprehensive Nuclear Test Ban Treaty, designed primarily to detect nuclear explosions, has proven to be a valuable resource for volcanic monitoring, detecting the infrasound signals of major eruptions around the world and providing data on volcanic activity in regions where dedicated monitoring networks are absent. Fact 77. Volcanic sunsets, when eruptions paint the sky. Among the most widely experienced and most aesthetically significant of all volcanic effects, the phenomena produced by volcanic activity that extend beyond the immediate vicinity of the erupting volcano to affect the experience of people living hundreds or thousands of kilometers away, who may never see the eruption itself, but who encounter its consequences in the quality of the light that reaches them, are the extraordinary atmospheric optical effects produced by the stratospheric aerosol clouds that major volcanic eruptions inject into the upper atmosphere, and whose specific interaction with sunlight produces, for months to years after the eruption, sunsets and sunrises of unusual intensity, duration, and chromatic richness that have been documented in the artistic, literary, and meteorological records of every major eruption in the historical period. The specific mechanism by which volcanic aerosols enhance sunset colors is the scattering of sunlight by the sulfate aerosol particles suspended in the stratosphere, particles of the specific size range that most effectively scatter the longer wavelengths of visible light, shifting the color of sunsets toward the deep reds, oranges, and purples that observers across the world recorded in the months following the eruptions of Krakatau in 1883, Tambora in 1815, and Pinatubo in 1991. Krakatau eruption of 1883 produced what may be the most extensively documented series of volcanic sunsets in history, the brilliant crimson and purple twilights that appeared in skies from London to New York in the months following the eruption, generating both scientific investigation. The British Royal Society conducted a systematic global survey of the optical phenomena, whose results constituted the first detailed scientific study of volcanic aerosol effects. An artistic response, the specific quality of the post-Krakatau light having been proposed as the specific visual reference for the blood-red sky in Edvard Munch's The Scream, whose 1893 composition date places it within the period when the atmospheric effects of the 1883 eruption were still detectable in Scandinavian skies, and whose specific dramatic intensity Munch himself described in terms consistent with the specific visual character of a volcanic twilight. Fact 78. The volcanic Pacific, an ocean built by fire. The Pacific Ocean, the largest ocean basin on Earth, covering approximately 165 million square kilometers and containing within its boundaries more than half of the world's total ocean water, is, in its fundamental geological structure, A volcanic creation. A basin floored entirely by oceanic crust, generated by the volcanic activity of the mid-ocean ridge system, and the hotspots that dot its interior, whose specific geological history, the continuous creation of new ocean floor at spreading centers, the subduction of old ocean floor at the ring of fire trenches that encircle it, and the construction of volcanic island chains and plateaus by hotspot and large igneous province activity throughout its interior, makes it the largest and most active volcanic province on Earth and the primary expression, at the planetary scale, of the plate tectonic processes that have continuously recycled the Earth's crust throughout the past 4 billion years. The specific age distribution of the Pacific Ocean floor, oldest in the northwest, where the ancient oceanic crust that formed at the East Pacific rise tens of millions of years ago, has been carried by plate motion to the margins of the basin, and youngest at the East Pacific rise itself, where new ocean floor is being created today at the fastest spreading rate of any mid-ocean ridge on Earth, approximately 15 centimeters per year. Records in the magnetic stripes of the ocean floor the entire history of Pacific spreading, a geological autobiography written in the specific magnetism of basaltic rock that was the key evidence for the theory of plate tectonics, and that continues, in the modern era, to provide the most detailed available record of the history of the Earth's surface. The Pacific hotspot trails, the lines of progressively older volcanic islands and seamounts that extend northwest from the current position of the Hawaiian hotspot, the Samoan hotspot, the Marquesas hotspot, and others, are the geological equivalent of the tracks left by a ship crossing the ocean. Recording in the specific ages and positions of volcanic structures, the rate and direction of Pacific plate motion over the past tens of millions of years, with a precision that no other geological tool can match. Fact 79, Volcanoes and Water, the Intimate Connection. The relationship between volcanic activity and water, the specific interactions between the Earth's volcanic systems and the hydrological cycle that covers its surface, is one of the most consequential and most multidimensional in all of Earth science, encompassing the volcanic origin of the oceans themselves, the role of water in triggering and shaping volcanic eruptions, the creation of volcanic lakes and geothermal springs whose specific chemical character supports unusual ecosystems, and the devastating consequences of the interaction between volcanic heat and ice or surface water in producing some of the most dangerous volcanic phenomena known. Water played a fundamental role in the most significant volcanic event in the Earth's history, the creation of the oceans. The specific origin of the Earth's surface water, the mechanism by which a planet formed in the inner solar system, where temperatures during accretion were too high for water ice to be stable, acquired the enormous volumes of water that now cover 71% of its surface, is a subject of ongoing scientific debate, with contributions attributed to the outgassing of water vapor from volcanic activity in the planet's early history. The delivery of water by asteroid and comet impacts during the late heavy bombardment, and possibly both processes operating simultaneously. The volcanic contribution to the Earth's water inventory, the release of water vapor as a primary component of volcanic gases throughout the planet's geological history, is certain and substantial, and the specific evidence for it is preserved in the isotopic composition of the Earth's ocean water, which falls between the isotopic signatures of volcanic-derived water and meteoritic water in a proportion consistent with a mixed volcanic and extraterrestrial origin. In the reverse direction, water plays a crucial role in generating and shaping volcanic eruptions. The presence of water in subducting oceanic crust and sediment lowers the melting point of the mantle wedge above, generating the magma that feeds the volcanoes of the Ring of Fire. The interaction of ascending magma with groundwater or surface water produces the phreatomagmatic eruptions of exceptional violence and fine ash production. And the melting of glacial ice by volcanic heat generates the specific catastrophic floods called Jökullaups that have repeatedly swept across Iceland's coastal plains in the historical period, carrying volumes of water comparable to the discharge of the Amazon River in events lasting only hours. Fact 80, the volcanoes at 80, 20 facts from the summit. 80 facts into the story of the volcanoes, and the summit is within sight. We have traveled the length and breadth of the volcanic world, from the lava lake of Nyiragongo, whose fluid fire has twice poured through the streets of a living city, to the infrasound monitoring stations that listen for eruptions in the frequencies below the threshold of human hearing, to the specific quality of light in the sky above London in the autumn of 1883 that may have given Edvard Munch the specific visual memory he needed to paint one of the most recognizable images in the history of human art. We have understood that the Pacific Ocean itself is a volcanic creation. Its floor built grain by grain and kilometer by kilometer from the basaltic magma of spreading centers and hotspots, whose combined output over billions of years has produced the largest single geological feature on the surface of the Earth. We have followed the water from the volcanic gases of the primordial Earth that may have built the oceans themselves, through the glacial floods of Iceland and the crater lakes of the tropics, to the specific moment when the meltwater of a Nevadan glacier poured into a volcanic vent, and the resulting explosion sent a lahar down the valley toward a sleeping town. 20 facts remain. They will carry us to the specific places and the specific people and the specific moments that the previous 80 have prepared us to understand, the final arguments in the case that the volcanic Earth has been making, fact by fact, across the entire length of this journey. The fires beneath the world have been burning for 4.5 billion years. They will be burning long after the last human voice has named them. This is explored during sleeping. Fact 81, the volcanic history of Venus, Earth's twin gone wrong. Venus, the second planet from the Sun, so similar to the Earth in size, mass and bulk composition that it has been described as the Earth's twin, and yet so profoundly different in its surface conditions. A surface temperature of approximately 465 degrees Celsius, an atmospheric pressure 90 times that of the Earth's surface, and a dense atmosphere of carbon dioxide and sulfuric acid clouds that makes it the most hostile planetary surface in the inner solar system, is a world whose specific character is, to a significant degree, the product of its volcanic history. A history that appears from the evidence available to spacecraft to have been dominated by an episode or episodes of catastrophic global volcanic resurfacing, whose specific consequences, including the massive outgassing of carbon dioxide and sulfur dioxide that created the runaway greenhouse effect responsible for the planet's extreme surface temperature, have made Venus the most dramatic example in the solar system of the long-term climate consequences of volcanic activity operating at the planetary scale. The surface of Venus, mapped in detail by the Magellan spacecraft between 1990 and 1994, using synthetic aperture radar capable of penetrating the planet's permanent cloud cover, is covered with volcanic features of extraordinary diversity and abundance, more than 1,600 major volcanoes, vast volcanic plains covering approximately 80% of the surface, enormous shield volcanoes comparable in scale to the Hawaiian chain, and a category of volcanic structure called coronae, circular to oval depressions surrounded by concentric fracture patterns, between 100 and 2,600 kilometers in diameter, that have no direct equivalent on Earth and whose specific formation mechanism, the upwelling of mantle plumes that deform the overlying lithosphere before sinking back, reflects the specific character of Venusian tectonics, which lacks the plate tectonic system of the Earth and instead appears to recycle its crust through a fundamentally different process of episodic overturn. The specific question of whether Venus is currently volcanically active, whether any of the eruptions that shaped its surface are ongoing rather than ancient, has been answered tentatively in the affirmative by the analysis of data from the European Space Agency's Venus Express mission, which detected thermal anomalies and changes in surface emissivity in volcanic regions consistent with recent or ongoing lava eruptions, and by a 2023 reanalysis of Magellan radar data that revealed the direct detection of a volcanic vent changing shape over a period of 8 months, the first direct evidence of active volcanism on Venus. Fact 82, the volcanic lakes of the world, calderas filled with water. The volcanic crater lakes and caldera lakes of the world, the bodies of water that occupy the summit craters, calderas, and explosion craters of volcanic systems across every volcanically active region on Earth, ranging in size from the small pools of a few meters diameter that occupy the craters of minor cinder cones to the vast caldera lakes of Toba in Sumatra and Taupo in New Zealand, whose surface areas are measured in hundreds of square kilometers, are among the most beautiful, most scientifically significant, and in some cases most hazardous of all the geological features produced by volcanic activity, their specific character reflecting the particular history of the volcanic system in which they have formed and the ongoing interaction between the volcanic heat and gases rising from below and the water and atmosphere above. Crater Lake in Oregon, the caldera lake that occupies the collapsed caldera formed approximately 7,700 years ago by the catastrophic eruption and subsequent collapse of the stratovolcano Mount Mazama, whose specific clarity and depth, at 594 meters, the deepest lake in the United States, make it one of the most spectacularly beautiful bodies of water on Earth, is perhaps the most visited volcanic lake in the world. Its extraordinary deep blue color, the product of the exceptional purity of its water and the specific absorption and scattering properties of water at great depth, making it a visual experience of rare intensity. Lake Toba in Sumatra, the caldera lake filling the enormous caldera produced by the supervolcanic eruption of approximately 74,000 years ago that was discussed in an earlier fact, covering an area of approximately 1,145 square kilometers and reaching a depth of 505 meters, is the largest volcanic lake on Earth and one of the largest lakes of any kind in Southeast Asia. Its specific dimensions reflecting the extraordinary scale of the eruption whose collapse created it. The most chemically extreme volcanic lakes are the hyperacid crater lakes found in the summit craters of active volcanoes, whose ongoing degassing maintains the lake water at pH values approaching zero. The lakes of Parás volcano in Costa Rica and Kawah Ijen in Indonesia, where concentrated sulfuric acid lakes of pH between 0 and 1 dissolve metal and create an environment hostile to essentially all life. Except for the specific extremophile microorganisms, whose discovery in these environments has continuously expanded the definition of the conditions under which life can persist. Fact 83. The people who predicted correctly volcanic science that saved lives. The history of volcanology contains, alongside its catalogue of disasters and failures of warning, a collection of specific episodes in which the correct application of scientific monitoring and hazard assessment provided sufficient warning of impending eruptions to save thousands of lives, episodes whose specific details deserve to be as widely known as the disasters they prevented. Both because they represent the specific achievements of individual scientists and institutions whose work directly saved human lives, and because they provide the most compelling available argument for the continued investment in volcanic monitoring and hazard assessment that the prevention of future volcanic disasters requires. The evacuation of the area around Mount Pinatubo before the June 1991 eruption, discussed in an earlier fact as the most successful large-scale volcanic evacuation in modern history, was made possible by the specific work of the team of volcanologists from the Philippine Institute of Volcanology and Seismology and the United States Geological Survey, who deployed a comprehensive monitoring network on the volcano in the weeks after its initial reawakening in April 1991, and interpreted the resulting data with sufficient accuracy to recommend the evacuation of approximately 60,000 people before the climactic eruption. The specific decision to show officials and the public the video footage of the 1980 Mount St. Helens eruption and the pyroclastic flows filmed by Keisha and Morris Kraft, who died at Unzen 12 days before Pinatubo's climactic eruption, was credited by the Philippine authorities with providing the specific visual evidence that motivated the unprecedented evacuation decision. The correct prediction of the 1991 eruption of Hekla in Iceland, a volcano whose specific behavior allowed volcanologists at the Icelandic Meteorological Office to issue a warning approximately 30 minutes before the eruption began, based on the characteristic seismic pattern that precedes Hekla eruptions, sufficient time to close the airspace over the volcano and alert aviation authorities, demonstrated that for some volcanic systems, the specific combination of long monitoring history and characteristic pre-eruptive signals allows a degree of short-term eruption prediction whose practical value for hazard management is very high, even if the same predictive precision cannot be achieved for most of the world's active volcanic systems. Fact 84. Volcanic glasses and tephrochronology, reading time in ash. Tephrochronology, the specific scientific technique of using the chemical fingerprint of volcanic ash layers deposited in sedimentary sequences, lake sediments, ice cores and peat bogs, to provide precise chronological markers for the dating and correlation of geological, archaeological and environmental records, is one of the most powerful and most versatile tools available to quaternary scientists working to reconstruct the sequence of events in the recent geological past, and one whose specific utility derives directly from two properties of volcanic ash that make it uniquely valuable as a chronological marker: the specific chemical composition of each eruption's ash, which varies in ways that allow individual eruptions to be identified and distinguished with high precision using geochemical analysis, and the near-instantaneous deposition of ash layers across the entire area affected by an eruption, which means that a specific ash layer represents effectively a single moment in time across its entire geographic distribution. The specific application of tephrochronology to the dating of archaeological sites, using the chemical fingerprints of known volcanic eruptions to establish the ages of the layers in which archaeological artifacts are found, has provided archaeologists with some of the most precisely dated sequences in the prehistoric record, particularly in regions where the absence of other datable materials would otherwise leave the chronology poorly constrained. In Iceland, where the historical record of eruptions extends back to the Norse settlement in approximately 874 CE, and the tephra layers produced by each eruption are preserved in the island's peat bogs and lake sediments with exceptional completeness, tephrochronology has provided a chronological framework of extraordinary precision for the study of Icelandic environmental and cultural history, including the specific dating of the settlement layer itself, whose position relative to the tephra layer produced by the eruption of Eyjafjallajökull in 877 CE allows the Viking settlement of Iceland to be dated with a precision of a few years, rather than the decades or centuries typical of archaeological chronologies from most other regions of the world. Fact 85. The volcanic history of the Moon, a cold furnace. The Moon, the Earth's only natural satellite, whose specific geological history represents one of the most thoroughly documented examples of planetary volcanic evolution available in the solar system, thanks to the combination of the 6 Apollo landing missions that returned samples of lunar rocks to Earth for laboratory analysis and the extensive orbital reconnaissance of the lunar surface by a series of robotic spacecraft, was, in its early history, a far more volcanically active world than it is today, its volcanic history leaving visible in the dark plains of the mare basalts that cover approximately 16% of its surface, a record of eruptions that occurred predominantly between approximately 3 and 4 billion years ago, and that transformed a cratered highland landscape into the specific pattern of dark lowland basins and bright highlands that gives the Moon its familiar face as seen from the Earth. The specific mechanism that drove lunar volcanism was the radioactive decay of heat-producing elements, uranium, thorium, and potassium, in the lunar interior, which maintained sufficient heat in the lunar mantle during the first billion years of the Moon's history to generate basaltic magma that erupted onto the surface through the large impact basins that had been created by the asteroid bombardment of the late heavy bombardment period. The Apollo samples returned from the lunar mare, the dark basaltic plains visible to the naked eye from the Earth, have been dated by radiometric methods and found to span an age range of approximately 3.1 to 3.9 billion years, consistent with a period of widespread volcanic activity that gradually declined as the lunar interior cooled and the radioactive heat sources decayed. The most recent volcanic activity on the Moon, tiny irregular patches of the surface, identified by the Lunar Reconnaissance Orbiter as irregular mare patches, whose specific texture and topographic freshness suggest an age of less than 100 million years, indicates that the Moon may not be entirely volcanically dead, and that small-scale volcanic eruptions may have occurred in the geologically recent past on a body long assumed to have been completely volcanically inactive for billions of years. Fact 86. The volcanic chain of the Andes, South America's spine of fire. The Andean volcanic arc, the chain of volcanoes extending approximately 7,000 kilometers along the western coast of South America, from Colombia in the north through Ecuador, Peru, Bolivia, Chile, and Argentina to the southern tip of the continent. Produced by the subduction of the Nazca Plate beneath the South American Plate along the Peru-Chile Trench, and comprising approximately 200 potentially active volcanoes, distributed in 4 distinct volcanic zones, separated by gaps where the specific geometry of the subducting plate suppresses volcanic activity, is the longest continental volcanic arc on Earth and one of the most volcanically diverse, its specific range of elevations, climates, and tectonic settings producing volcanic systems of extraordinary variety, whose behavior spans the full spectrum from the highly explosive rhyolitic eruptions of the southern Andes to the persistently active andesitic stratovolcanoes of Ecuador and Colombia. The specific volcanic hazards of the Andean arc are shaped by its unique combination of high altitude and glacial ice. The numerous volcanoes in the central and southern Andes that rise above the permanent snowline carry on their upper flanks significant volumes of glacial ice and snow, whose interaction with volcanic heat and erupted material generates lahars of exceptional size and mobility. Capable of traveling hundreds of kilometers from the erupting volcano through the river valleys that descend from the Andean highlands to the Pacific coast and the Amazon basin. The specific example of Cotopaxi in Ecuador, a nearly perfectly symmetrical stratovolcano rising to 5,897 meters above sea level, topped by a glacier of approximately 12 square kilometers, and one of the most active volcanoes in the Andes, with approximately 50 eruptions in the historical record, illustrates the specific character of the Andean volcanic hazard with particular clarity. Cotopaxi's eruptions have repeatedly generated large lahars that have descended the valleys on its flanks to distances of more than 300 kilometers, and the specific concern about its future eruptions is focused above all on the potential for a major eruption to rapidly melt substantial portions of its summit glacier, generating lahars of sufficient volume to threaten the approximately 300,000 people living in the valleys downstream. Fact 87. The science of lava: what happens when rock flows. The specific physical and chemical behavior of lava, the molten rock that emerges at the Earth's surface during volcanic eruptions, and whose cooling and solidification produces the volcanic rock types that constitute the oceanic crust, the volcanic island chains, the flood basalt provinces, and the countless individual lava flows that have been erupted across the surface of the Earth throughout its geological history, is a subject of scientific investigation whose specific complexity, spanning the disciplines of petrology, geochemistry, fluid dynamics, and materials science, has generated an enormous body of research whose practical applications range from the prediction of lava flow behavior during volcanic emergencies to the understanding of the large-scale geological processes that have shaped the Earth's surface over billions of years. The viscosity of lava, its resistance to flow, the property that most directly controls how fast it moves, how far it travels, and what structures it produces as it cools, varies by more than 10 orders of magnitude across the full range of lava compositions encountered on Earth, from the extraordinarily fluid carbonatite lavas of Old Doinyo Lengai in Tanzania, which flow at temperatures of approximately 510 degrees Celsius and viscosities comparable to motor oil, to the thick, slow-moving rhyolitic lavas of supervolcanic systems, whose viscosity at eruption temperature is comparable to solid glass, and which advance at rates of meters per day rather than the meters per second of the most fluid basaltic flows. The specific structures that lava creates as it flows and cools are direct expressions of its viscosity and the specific conditions of its emplacement. The ropey, smooth surface of Pahoehoe lava, formed when a low-viscosity basaltic flow develops a solidified skin that is folded by the continued movement of the liquid beneath. The rough, jagged surface of our lava, formed when the same basaltic composition is subjected to higher strain rates that fragment the solidifying surface rather than folding it. The blocky lava of more viscous andesitic flows, whose thick, slowly cooling exterior breaks into angular blocks as the interior continues to move. And the spectacular columnar jointing of thick basaltic flows that cool slowly and evenly, the contraction during cooling creating the regular hexagonal columns whose specific geometry, the product of the mathematics of crack propagation in a uniformly cooling medium, produces the extraordinary visual regularity of structures like the Giant's Causeway in Northern Ireland and Fingal's Cave in Scotland. Fact 88. Volcanic disasters of the ancient world, history written in ash. The geological record of volcanic eruptions in the ancient world, the ash layers, lava flows, and volcanic deposits that preserve the evidence of eruptions that occurred before the development of writing, before the keeping of systematic records, and in some cases before the presence of human observers capable of recording what they witnessed, contains the evidence of events whose specific scale and whose specific consequences for the human populations of the ancient world can be reconstructed with increasing precision and increasing confidence from the convergence of geological, archaeological, and genetic evidence accumulated by researchers over the past several decades. The Minoan eruption of Santorini, the Bronze Age catastrophe whose possible relationship to the decline of Minoan civilization and the legend of Atlantis was discussed in an earlier fact, is the most thoroughly investigated prehistoric volcanic disaster in the ancient Mediterranean. But the geological record of the Holocene period contains evidence of numerous other eruptions of comparable or greater magnitude, whose specific consequences for the human populations they affected have left traces in the archaeological and genetic record that researchers are only beginning to systematically investigate. The eruption of the Ilopango caldera in El Salvador in approximately 431 CE, a VEI6 event that buried a large area of Central America under volcanic ash and may have depopulated the Maya heartland of the Guatemalan highlands for several generations, has been identified by archaeologists as a potential factor in the specific demographic and political disruptions of the Maya Classic period, whose causes have long been debated. The eruption of Pektu Mountain on the border between North Korea and China in approximately 946 CE, the Millennium Eruption, one of the largest volcanic events of the past 2,000 years, has been proposed as a contributing factor to the specific political disruptions of the Balhae Kingdom in Manchuria and the Goryeo Kingdom in Korea that occurred in the same period. Each of these ancient volcanic disasters is a reminder that the geological record contains a history of human experience whose specific dimensions, the specific fear, the specific displacement, the specific cultural and demographic consequences of volcanic catastrophe are recoverable, if only partially, from the evidence that the eruptions themselves have left behind. Fact 89. The future of volcanic monitoring, eyes on the Earth. The specific trajectory of volcanic monitoring science in the early 21st century, the development of new instruments, new analytical techniques, and new computational tools whose combined application to the world's volcanic systems is transforming the quantity, quality, and interpretability of the monitoring data available to volcanologists and civil protection authorities. Offers genuine grounds for optimism about the future capacity to forecast volcanic eruptions with sufficient accuracy and lead time to protect the populations most at risk. While the specific scale of the challenge, more than 800 volcanoes that have erupted in the past 10,000 years, distributed across the volcanic regions of every continent and ocean, many of them in developing nations whose monitoring infrastructure is minimal, ensures that the gap between the monitoring capabilities available at the best instrumented volcanoes and those available at the most dangerous and least monitored will remain a fundamental challenge for volcanic risk management for decades to come. The most significant recent advance in volcanic monitoring capability has been the deployment of satellite-based monitoring systems whose specific capacity to observe volcanic ground deformation, gas emissions, thermal anomalies, and ash plume development over the entire surface of the Earth on a continuous basis has transformed the monitoring of remote and poorly instrumented volcanic systems. The Sentinel satellite constellation of the European Space Agency, whose Sentinel-1 radar satellites provide ground deformation measurements across all of the Earth's volcanic regions on repeat cycles of 6 to 12 days, and whose Sentinel-5P satellite provides continuous measurements of volcanic sulfur dioxide emissions globally, has made it possible for the first time to detect signs of volcanic unrest at volcanoes that have no ground-based monitoring networks. Providing a global baseline of volcanic activity, data whose specific applications for early warning of unrest at previously unmonitored volcanoes are already being demonstrated in case studies from volcanic systems in Africa, South America, and the remote Pacific. The integration of satellite monitoring data with artificial intelligence systems capable of automatically detecting and classifying volcanic signals in the vast data streams produced by global monitoring networks represents the specific frontier of current volcanic monitoring research, whose specific promise is the automated, continuous assessment of volcanic hazard across the entire surface of the Earth. Fact 90. The volcanic soil of civilization, feeding the world from fire. The specific relationship between the volcanic geology of the Earth's most productive agricultural regions and the specific civilizations that those regions have supported throughout human history, the degree to which the fertility of volcanic soils has been, across a range of cultures and periods, the agricultural foundation on which some of the most complex, most populous, and most historically significant human societies were built, represents one of the most profound and most consistently underappreciated dimensions of the long relationship between volcanic geology and human civilization. The volcanic soils of Java, the product of the island's extraordinary density of active volcanoes, whose repeated eruptions have deposited layers of nutrient-rich ash across the island's landscape throughout the Holocene, support, as noted in an earlier fact, a population density that makes Java one of the most densely populated large islands on Earth. Its agricultural system of wet rice cultivation producing yields per hectare that are among the highest in the world and that have supported, for more than a millennium, the succession of kingdoms and empires whose specific cultural achievements, the temples of Borobudur and Prambanan, the classical Javanese literary and artistic traditions, the sophisticated hydraulic engineering systems that transformed the volcanic landscape into the terraced rice paddies still visible today, represent the specific cultural flowering that the volcanic agricultural abundance of the island made possible. The volcanic soils of Central America, formed from the ash deposits of the long chain of active volcanoes running along the Pacific coast of Guatemala, El Salvador, Nicaragua, and Costa Rica, have supported dense agricultural populations since the pre-Columbian period, providing the specific ecological foundation for the Maya civilization in the highlands and the succession of chiefdoms and states in the Pacific lowlands, whose specific development was shaped throughout by the twin influences of volcanic fertility and volcanic hazard. The coffee that is grown on the volcanic slopes of Ethiopia, Guatemala, Colombia, and Hawaii, the specific flavor profiles that coffee connoisseurs attribute to the mineral richness and drainage properties of volcanic soils, is perhaps the most globally distributed and most daily experienced of all the products of volcanic geology, a commodity consumed by hundreds of millions of people who are, with each cup, experiencing in however indirect a form the specific chemistry of the Earth's volcanic interior, translated by millennia of soil formation and generations of agricultural practice into the most widely consumed psychoactive beverage in the world. Fact 91. The volcanic islands of the Pacific, cultures born on fire. The volcanic islands of the Central and Western Pacific, the scattered archipelagos of Hawaii, Samoa, Tonga, Vanuatu, the Solomon Islands, Fiji, and the hundreds of smaller island groups whose specific geological origins as the surface expressions of mantle hotspots or subduction zone volcanic arcs place them, isolated by vast expanses of open ocean, at the furthest reach of human settlement in the prehistoric period. Were colonized by the Polynesian and Melanesian peoples, whose specific maritime technology, whose extraordinary navigational knowledge, and whose particular cultural relationship with the ocean and its islands represents one of the greatest achievements in the history of human exploration. A settlement of the world's largest ocean that was completed by approximately 1000 CE, and that placed human communities on virtually every habitable volcanic island in the Pacific centuries before European ships reached the region. The specific cultural relationship of Pacific Island peoples with the volcanic landscapes they inhabited was not incidental but foundational. The volcanic geography of the islands shaped every dimension of island life, from the specific agricultural systems developed on the fertile volcanic soils to the mythological traditions that explained the origin of the islands and the ongoing activity of the volcanic systems that continued to reshape them. In Hawaii, the volcanic landscape was incorporated into the most fundamental levels of the cosmological tradition. The creation chants of the Cumulipo describe the emergence of the islands from the ocean as a volcanic process. The specific activity of the volcanic system is explained through the mythology of Pele and her family, and the specific locations of the most volcanically active features of the landscape, the Kilauea caldera, the lava fields of Puna. The fiery entry of lava into the sea are identified as the specific dwelling places and battlegrounds of volcanic deities, whose stories encode both the geological behavior of the volcanic system and the specific cultural values of a society that had learned, over many generations of intimate coexistence with volcanic activity, exactly what it meant to live on an island built by fire. The specific ecological knowledge that Pacific Island peoples developed about the volcanic landscapes they inhabited, the understanding of which soils were most fertile, which slopes were most hazardous, which springs were safe and which were contaminated by volcanic gases, represents a tradition of empirical knowledge about volcanic environments accumulated over centuries of practical engagement with geological systems whose behavior was, for the communities depending on them, a matter of daily life and survival. Fact 92. The architecture of volcanic risk, who lives in the hazard zone. The specific distribution of the world's population within volcanic hazard zones, the demographic pattern of who lives in closest proximity to the most dangerous volcanic systems, and why reveals, with uncomfortable clarity, one of the most consistent and most consequential inequalities in the global distribution of geological risk. The systematic concentration of the most vulnerable populations in the highest hazard zones, a pattern produced not by ignorance or irrationality, but by the specific intersection of the agricultural fertility of volcanic soils, the historical patterns of land tenure and economic opportunity that have driven poor populations toward the most productive but most hazardous agricultural environments, and the specific failure of the economic and political systems of volcanic nations to provide viable alternatives for the communities most at risk. The approximately 800 million people who currently live within 100 kilometers of an active volcano, approximately 1 in 10 of the world's population, are not evenly distributed across the volcanic regions of the globe. The highest concentrations of volcanic risk are in the densely populated volcanic zones of Southeast Asia, Java, Bali, Sumatra, the Philippines, where the combination of extremely active volcanoes and some of the highest rural population densities on Earth creates a specific risk landscape whose aggregate exposure to volcanic hazard dwarfs that of the more thoroughly monitored volcanic systems of North America and Europe. The specific communities most concentrated in volcanic hazard zones within these regions are typically the poorest and least politically powerful, smallholder farmers whose specific livelihoods depend directly on the agricultural productivity of volcanic soils, and who lack the economic resources to purchase land in less hazardous locations, even if such land were available and affordable. The specific consequence of this distribution is that the volcanic disasters that produce the highest death tolls, the eruptions that kill tens of thousands of people, occur overwhelmingly in the developing world, while the volcanic disasters that receive the most scientific attention and the most extensive monitoring resources occur in the high-income volcanic nations of North America, Europe, and Japan. A disparity in attention and investment, whose specific human consequences are measured in the preventable deaths that inadequate monitoring and warning systems fail to prevent. Fact 93: Volcanoes and climate change, the complex interaction. The specific relationship between volcanic activity and climate change, the ways in which the Earth's volcanic systems interact with the ongoing anthropogenic warming of the climate system, and the ways in which climate change may in turn affect the behavior of volcanic systems, is a subject of active and increasingly urgent scientific research, whose specific conclusions challenge some widely held assumptions about the independence of geological and climatic processes, and raise important questions about the feedbacks between the Earth's interior and its surface in a warming world. The specific contribution of volcanic activity to the current episode of climate change is negligible by comparison with the contribution of anthropogenic greenhouse gas emissions. The global volcanic output of carbon dioxide, estimated at approximately 300 million metric tons per year from all volcanic sources combined, is less than 1% of the approximately 37 billion metric tons of CO2 emitted annually by human activities, a comparison that definitively refutes the specific claim, sometimes encountered in public discussions of climate change, that volcanic emissions are a significant driver of the current warming. In the reverse direction, however, the specific effects of climate change on volcanic activity are the subject of genuine scientific concern. The melting of glaciers and ice sheets that is already underway as a consequence of anthropogenic warming removes mass from the surface of the Earth in volcanic regions, reducing the confining pressure on the underlying magma systems and potentially facilitating the ascent of magma toward the surface, a process whose specific geological evidence, including a documented increase in volcanic activity in Iceland following the last deglaciation approximately 12,000 years ago, suggests that the ongoing and projected melting of the world's glaciers and ice caps could, over timescales of decades to centuries, modestly increase the frequency of volcanic eruptions in glaciated volcanic regions. The melting of permafrost in Arctic and subarctic volcanic regions may similarly reduce the confining pressure on shallow hydrothermal systems and increase the frequency of phreatic eruptions, steam explosions driven by the vaporization of groundwater in contact with volcanic heat, in regions where permafrost has previously acted as a cap on these systems. Fact 94: the rarest lava on Earth, carbonatite and the singing volcano. Old Doinyo Lengai, the active stratovolcano in the Gregory Rift of northern Tanzania, rising to 2,962 meters above the floor of the East African Rift Valley, and visible on clear days from the shores of Lake Natron, whose pink-white surface of sodium carbonate evaporite lies immediately to the volcano's north, is unique among all the active volcanoes on Earth in erupting carbonatite lava. A lava type so compositionally different from all other volcanic products on the planet that its specific chemical character places it outside the normal classification of igneous rocks and raises fundamental questions about the specific geological processes that generate it. Carbonatite lava, composed primarily of calcium, sodium, and potassium carbonates rather than the silicate minerals that constitute all other terrestrial lavas, is erupted at temperatures of approximately 510 to 600 degrees Celsius, far lower than any silicate lava, and with a viscosity comparable to water, making it the most fluid lava known on Earth. When erupted at the surface, carbonatite lava appears not red or orange like conventional basaltic lava, but black, the specific optical properties of the molten carbonate giving it a color and texture that observers have compared to black engine oil or liquid tar rather than conventional lava. As the carbonatite cools and begins to solidify, it undergoes a series of chemical reactions with atmospheric moisture and carbon dioxide that progressively alter its color from black through gray to the brilliant white of the weathered carbonatite deposits that cover much of the volcano's flanks, giving Old Doinyo Lengai a surface of extraordinary visual strangeness, a volcanic landscape of white, gray, and black that looks, to observers accustomed to the red and brown of conventional volcanic terrain, entirely unlike any other active volcanic landscape on Earth. The Maasai people who have lived in the shadow of Old Doinyo Lengai for generations call it the Mountain of God, a name whose specific resonance, the identification of this geologically unique and visually extraordinary mountain with the divine, expresses with precision the specific awe that the volcano's singular character has generated in the human community most intimately acquainted with it. Fact 95: the volcanic record in ice, frozen history. The ice cores extracted from the great ice sheets of Greenland and Antarctica, the cylindrical samples of compacted snow and ice, drilled from depths of up to more than 3 kilometers, representing the accumulated snowfall of up to 800,000 years of Arctic and Antarctic winters, and preserving within their layered structure a continuous chemical record of the atmospheric composition, temperature, and particulate content of the air that was trapped as each layer of snow fell and compacted into ice, are among the most important and most versatile archives of past environmental conditions available to Earth scientists, and they are also, unexpectedly, among the most comprehensive records of global volcanic activity available for the past 800,000 years. The specific chemical signature of volcanic eruptions preserved in ice cores is the sulfate signal, the layer of elevated sulfate concentration that marks, in the ice core record, the deposition of volcanic sulfuric acid aerosols produced by the conversion of eruption-derived sulfur dioxide in the stratosphere, and whose specific concentration, stratigraphic position, and geographic distribution across ice cores from both hemispheres provides information about the timing, magnitude, and latitudinal position of the eruption that produced it. The ice core volcanic record has been used to identify and date eruptions that have no historical documentation, including the mystery eruption of 536 CE, whose location was debated for decades before the chemical fingerprint of its ash, preserved in a Greenland ice core, allowed its identification as an Icelandic eruption, and to establish the precise timing of eruptions whose historical dating was uncertain. The specific value of the ice core volcanic record for climate science lies in the specific coincidence it reveals between the timing of major volcanic sulfate signals and the temperature anomalies recorded by the ice core's isotopic composition, a direct, quantitative demonstration of the relationship between volcanic eruptions and climate cooling, whose specific precision and temporal resolution is available from no other geological archive. And that has been used to calibrate the climate models on which projections of future volcanic climate impacts are based. Fact 96: the volcanoes of the deep past, Archean fire. The volcanic history of the Earth in its earliest chapters, the volcanic activity of the Archean eon, the period from approximately 4 to 2.5 billion years ago that encompasses the first half of the Earth's existence, and during which the specific conditions of temperature, atmospheric composition, and geological process that characterized the early Earth produced a volcanic landscape fundamentally different from anything observable in the present, is the most remote and most incompletely known chapter of the planet's geological biography, reconstructed from the specific rocks of the Archean cratons that preserve the oldest surviving fragments of the Earth's early crust and whose specific character, different in mineralogy and texture from any volcanic rock produced in the modern Earth, records the specific conditions of a hotter and more vigorously convecting planet whose volcanic activity operated on a scale and at a style that has no direct modern analogue. The most distinctive rock type of the Archean volcanic record is the komatite, a volcanic rock produced by the eruption of ultramafic magma, richer in magnesium and iron and poorer in silica than any common modern lava type, at temperatures estimated at between 1,600 and 1,800 degrees Celsius, temperatures far higher than any magma erupted in the modern Earth, reflecting the specific character of a mantle that was in the Archean several hundred degrees hotter than its present state, and therefore capable of producing magmas of compositions that the modern Earth's mantle is too cool to generate. The specific texture of komatites, the distinctive spinifex texture, named for the spiky Australian grass it resembles, produced by the extremely rapid cooling of the ultra-high temperature melt, is diagnostic of Archean volcanic environments and has been found in ancient rock sequences on every continent, each occurrence a preserved sample of an eruptive process that ended billions of years ago, and that the modern Earth, its interior having cooled through billions of years of heat loss, is no longer capable of reproducing. The Archean volcanic record is, in this sense, the most direct evidence available that the Earth has been cooling throughout its history, its volcanic style evolving as its interior temperature has declined from the specific extremes of the early planet toward the specific character of the modern volcanic Earth. Fact 97: the survivors' stories from the shadow of eruptions. The human literature of volcanic survival, the specific accounts left by individuals who were present at major volcanic eruptions and survived to record their experience, from the letters of Pliny, the Younger describing the 79 CE eruption of Vesuvius, to the testimonies of survivors of the 1902 St. Pierre disaster and the 1985 Armero Laha. From the oral traditions of Hawaiian and Japanese and Indonesian communities, whose collective memory preserves the specific experience of past eruptions in forms accessible to later generations. constitutes one of the most intimate and most revealing documents available for understanding the human dimension of volcanic disaster, the specific texture of an experience whose combination of sudden overwhelming sensory intensity, radical disruption of the expected order of the world, and confrontation with the absolute indifference of geological process to human life and human meaning has generated, in the survivors who have found the words for it, some of the most powerful accounts of extreme natural experience in the entire literature of the human encounter with the natural world. The account of Pliny the Younger, written to the historian Tacitus at Tacitus's specific request, describing what Pliny had witnessed from across the Bay of Naples during the Vesuvius eruption and what his uncle had experienced in his fatal approach to the erupting volcano, is the founding document of this literature, establishing in its specific combination of scientific observation and human narrative the dual register that the best writing about volcanic experience has maintained ever since. Pliny describes the specific appearance of the eruption column, comparing it to a pine tree for its specific shape of a tall trunk supporting a broad canopy of dispersed ash, with the observational precision of a natural historian, while simultaneously recording the specific human responses of the people around him. The panic, the darkness, the ash falls that threatened to bury those who stopped moving, the specific prayers and cries of those who believed the end of the world had come. The survivor accounts of the 1902 St. Pierre disaster, above all the specific testimony of Lugia Silbaris, the prisoner whose stone cell protected him from the pyroclastic surge that killed 30,000 of his neighbors, belong to the same tradition. The specific evidence, preserved in a single human voice, of what it is to be present at the intersection of human life and geological violence and to come through on the other side. Fact 98, the most active volcano you've never heard of, Kilauea's long eruption. Kilauea, the shield volcano on the southeastern flank of Mauna Loa on the Big Island of Hawaii, whose summit caldera, HRLEM, a letter 2BBUM, a letter 2BBU, is identified in Hawaiian tradition as the primary home of the volcano goddess Pele, and whose East Rift Zone produced one of the longest duration volcanic eruptions in the historical record, a continuous eruption from the Po event that lasted from January 3, 1983 to September 4, 2018, a period of approximately 35 years, is probably the most continuously observed and most thoroughly scientifically documented active volcanic system on Earth, and yet remains, outside of Hawaii and the volcanological community, considerably less famous than the more sporadically dramatic volcanoes of the Ring of Fire, whose explosive eruptions generate the specific visual and emotional intensity that the global media requires for sustained coverage. The 35-year Po eruption, which added approximately 230 hectares of new land to the southern coast of the Big Island through the repeated advance of lava flows to the ocean, destroyed approximately 215 structures, including entire neighborhoods in the Puna district, buried approximately 14 kilometers of highway under lava, and produced the world's largest collection of continuous volcanic monitoring data from a single erupting vent. Was succeeded by the 2018 Lower East Rift Zone eruption, in which the opening of new fissure vents in a residential area of Leilani Estates sent lava flows through the neighborhood over a period of 3 months, destroying more than 700 homes and fundamentally transforming the landscape of Lower Puna in ways that will persist for centuries. The specific human experience of the 2018 eruption, documented in real time on social media, in newspaper accounts, and in the specific testimonies of the residents who watched their homes disappear under advancing lava flows, while simultaneously acknowledging the specific geological grandeur of the process consuming them, captures something essential about the relationship between human beings and the volcanic landscapes they choose to inhabit. The specific coexistence of loss and wonder, of grief for what is destroyed and awe at the specific beauty of the destruction, that has characterized the human encounter with volcanic activity across every culture and every century in which it has occurred. Fact 99, what volcanoes have made a reckoning. The specific balance sheet of what volcanic activity has contributed to the Earth and to the human civilization that has built itself on the Earth's surface. The accounting of creation and destruction, of gift and catastrophe, of the specific long-term geological generosity, and the specific short-term geological violence that constitute the full range of volcanic consequence, is one of the most important and most genuinely difficult exercises available to anyone who has followed the volcanic story from its geological beginnings to its human present. On the side of creation, the case is overwhelming in its scale. Volcanic activity built every ocean floor on the planet, created every volcanic island from Hawaii to Iceland, produced the fertile soils that have supported the agricultural foundations of some of the most significant civilizations in human history, generated the atmosphere that every living organism breathes, may have provided the specific chemical environments in which life itself first assembled, delivered the diamonds from the mantle to the surface, produced the obsidian that our prehistoric ancestors used to make the sharpest cutting tools available before the development of metallurgy, gave us the geothermal energy that Iceland uses to heat its homes and power its industry, and created landscapes of such extraordinary beauty that the human response to them, the mythology, the art, the literature, the pilgrimage, constitutes one of the richest and most consistent traditions in the cultural history of the species. On the side of destruction, the case is also powerful in its specific human weight. Volcanoes killed the people of Pompeii and St. Pierre, buried Armero in a river of mud, sent lahars through the streets of Goma, launched the famine that killed a fifth of Iceland's population, injected the stratospheric veil that stole the summer of 1816 from the farmers of New England and the poets of Lake Geneva, and may have reduced the entire human species to a few thousand individuals in the aftermath of Toba. Both sides of this accounting are real. Both sides are necessary to the full understanding of what a volcano is, and what it means that we live on a planet that has been making and unmaking itself with fire since before the first living cell divided in the darkness of a hydrothermal vent 4 billion years ago. Fact 100, the fire that made the world what remains. Close your eyes, breathe slowly. The earth beneath you is not still. At this moment, as you lie in the dark and let the day dissolve, the mantle is moving slowly, imperceptibly, at the rate of a fingernail growing, driven by the heat of a planet that has been cooling for 4.5 billion years and has not finished yet. Somewhere on the surface of this moving world, lava is reaching the sea and building a new coastline grain by grain. Somewhere, a monitoring seismograph is recording the specific pattern of earthquakes that precedes a magma body moving toward the surface. Somewhere, a volcanologist is reading the data on a screen in the darkness, making the specific judgment that the science and the uncertainty and the weight of responsibility combine to require, trying to determine whether the mountain above the sleeping city is preparing something that the sleeping city needs to know about. The volcanoes that we have visited across these 100 facts, from Vesuvius to Yellowstone, from Krakatau to Kilauea, from the lava lake of Nyiragongo to the frozen summit of Erebus, from the primordial outgassing that built the first atmosphere to the sulfate aerosols that painted the skies of London crimson in the autumn of 1883, are not curiosities or anomalies in the story of a planet that would otherwise be safe and still. They are the planet's story. They are how the Earth speaks, how it breathes, how it moves material from its interior to its surface and back again, in cycles that operate on timescales no human civilization has yet been old enough to witness in their entirety. The specific fire at the center of the Earth, the heat left over from the violence of planetary formation, the heat generated by the slow decay of radioactive elements distributed through the mantle and the crust, is 4.5 billion years old and is still tonight, driving the convection that moves the plates, feeding the magma chambers that fill and empty beneath the volcanoes of the Ring of Fire, maintaining the lava lake of Erebus in its Antarctic crater. Building the seamount of L Omicron letter 2BB, IHI toward a surface it will not reach for 10,000 years. We are alive on a living planet. The fires beneath us are the same fires that built the ground we stand on, that created the air we breathe, that may have assembled the first molecules capable of copying themselves in the hot, dark, mineral-rich water of a seafloor vent 3.5 billion years ago. To lie on the surface of this planet and listen to it, to understand, even partially, what the volcanic record means and what the volcanic future holds, is to be present at a story of incomprehensible scale and incomprehensible age, that is, nonetheless, the story of the specific ground beneath your specific body on this specific night. The fires have not gone out. They will not go out in any time that a human being can meaningfully imagine. And in their persistence, in the specific ongoing generosity of a planet that has been making new land and new soil and new atmosphere for longer than life itself has existed, there is something that is not quite comfort but is very close to it, the specific reassurance of knowing that the world is larger and older and more patient than any of the catastrophes it periodically visits upon its surface, and that the ground beneath you, for all its fire, intends to be here for a very long time. This is explored during sleeping,